In December of 1963, inside a windowless conference room at the Statler Hilton Hotel in Dallas, Texas, a young mathematician stood before a restless crowd. The audience had come for quasars. They had come because earlier that year, astronomers had detected radio sources at distances so staggering, with luminosities so violent that no known physics could explain them. 320 physicists and astronomers had descended on Dallas to argue about these impossible objects burning at the edges of the observable universe. And now, wedged into the programme between the headline debates, a 29-year-old New Zealander named Roy Kerr was given 10 minutes to present a piece of mathematics. He spoke quietly. The equations were dense. Within 3 minutes, figures in the back rows began checking their watches. A few slipped out for coffee. Others tilted back in their chairs and let their eyes drift closed. The particular half-sleep of a conference attendee who has already decided that the current speaker is not the one they came to hear. Kerr continued. He was describing an exact solution to Einstein's field equations for a rotating mass. He was explaining that, unlike every solution that had come before it, this one did not require the simplifying assumption that the central object stands still. He was telling them that he had solved, in closed form, the geometry of spacetime around a spinning body, around anything that rotates, which is to say, around nearly everything in the cosmos. But the room had made up its mind. Then a figure in the middle rows rose to his feet. Achilles Papapetrou, Greek, grey-haired, one of the elder statesmen of general relativity, began speaking before the polite applause had even finished. His voice carried the sharp urgency of someone who has just realised that the rest of the room has missed something dangerous. Papapetrou did not praise Kerr's cleverness. He did not offer collegial encouragement. He told the audience, in terms too blunt to be misunderstood, that what they had just witnessed was one of the most important exact solutions ever derived in the 60-year history of general relativity. He told them that Kerr had done what generations of physicists had attempted and failed to do. He told them to sit down and pay attention. The room went quiet. People stopped rustling their papers. The men who had slipped out for coffee did not come back in time. That evening, in conversation scattered across the hotel lobby and the downtown Dallas streets, a different kind of murmur began to spread. Kerr's solution was not a curiosity. It was not an incremental refinement. It was a window into the interiors of every rotating object massive enough to collapse under its own gravity, which is to say, a window into the hearts of most of the black holes that actually exist. And the geometry Kerr had uncovered was deeply, structurally wrong. Wrong in a way that physics was not prepared to confront. Because the singularity, the point of infinite density that was supposed to sit at the centre of every collapsed star, was not a point at all. It was a ring. And through the centre of that ring, Kerr's mathematics suggested there was something else. Not a wall, not an ending, a passage, a corridor of space-time leading somewhere that should not, by any reasonable interpretation of physical law, exist. This documentary is the story of that corridor, and of the 60 years physicists have spent arguing about whether anything or anyone could survive the journey through it. To understand what Kerr found in the summer of 1963, you first have to feel what rotation does to space-time, not as an abstraction, not as a line of mathematics on a chalkboard, but as a physical, visceral phenomenon that operates on your body right now, at this very moment, even as you sit still. Consider the Earth beneath you. It is rotating. One full turn every 23 hours and 56 minutes, spinning west to east, dragging everything on its surface along for the ride. You do not feel this motion directly, because you have been moving with it since birth, but the rotation is there, and it is doing something to the fabric of space-time in your immediate vicinity. Picture a gyroscope. A simple one. A wheel spinning on an axis, mounted in a frame that allows it to point in any direction. If you set such a gyroscope spinning in empty space, far from any mass, its axis will stay fixed, locked onto a single direction relative to the distant stars, even as you rotate the frame around it. This is the principle that guides satellites, missiles, inertial navigation systems. A spinning gyroscope resists being pushed. Its axis remembers where it was pointing. But place that gyroscope in orbit around the Earth. A low orbit, perhaps 650 kilometers up, crossing directly over the poles, and something subtle begins to happen. The axis drifts, very slightly, imperceptibly at first. Over the course of a year, the gyroscope's orientation shifts by a tiny angle, so small it is measured not in degrees, but in milliseconds. A millisecond is 1/3,600th of a degree. It is the angle subtended by a human hair seen from 10 miles away. And yet the drift is real. The drift is there. And the drift tells you something profound about the nature of rotating mass. This is the lens-Thirring effect, first predicted by the Austrian physicists Joseph Lenz and Hans Thirring in 1918, 3 years after Einstein's general theory of relativity first described gravity not as a force, but as the geometry of spacetime itself. Lenz and Thirring worked out a consequence of Einstein's equations that had not been fully appreciated. A stationary mass warps spacetime by its presence, yes, bending the paths of light and matter around it, but a rotating mass does something more. A rotating mass drags spacetime with it, not metaphorically, not approximately, actually. The rotation of the mass reaches out and grips the fabric of spacetime and twists. Everything in the vicinity, light, matter, the gyroscopes of orbiting satellites, is pulled ever so slightly in the direction of the spin. For nearly 90 years this prediction remained unconfirmed. The effect was too small, the precision required too far beyond existing technology. Then, on the 20th of April 2004, a spacecraft called Gravity Probe B lifted off from Vandenberg Air Force Base in California, carrying 4 gyroscopes more perfect than any that had ever been built. These were not ordinary gyroscopes. They were spheres of fused quartz the size of ping-pong balls, polished to within 40 atomic layers of perfect roundness, coated with a microscopically thin layer of niobium, and cooled to within 2 degrees of absolute zero so that they would become superconducting. They were the most spherical objects ever manufactured by human beings, and they were designed for one purpose: to detect the whisper of frame dragging exerted by Earth's rotation, a whisper so faint that, over the course of an entire year, it would shift a gyroscope's axis by only 39 milliseconds. Data collection began on the 28th of August 2004. For nearly a year, as Gravity Probe B circled the Earth in its polar orbit, its 4 gyroscopes spun silently in their housing, and sensors monitored their axes with a precision never before achieved in any experiment. And then the waiting began. The data was messy. Unexpected torques from static electrical charges on the spacecraft had introduced noise. Engineers at Stanford spent 5 years developing new techniques to tease the relativistic signals out from the interference. Careers were spent. Frustrations mounted. For a time, critics wondered whether the mission had failed entirely. But on the 4th of May 2011, Stanford and NASA announced their results. The geodetic drift, the precession caused by Earth's simple mass, had been measured at negative 661.8 milliseconds per year, within 18 milliseconds of the prediction. And the frame-dragging drift, the twisting, the lens-Thirring effect, the fingerprint of Earth's rotation on the geometry of spacetime itself, had been measured at negative 37.2 milliseconds per year. The prediction was negative 39.2 milliseconds per year. The measurement agreed to within 2 milliseconds. Frame dragging was real. This may sound like an obscure confirmation of an obscure effect, a minor footnote to Einstein's legacy, of interest only to specialists. But to understand the Kerr metric, to understand the ring singularity, to understand the corridor that may or may not open through the heart of every rotating black hole in the cosmos, you must first feel what this means. When a mass rotates, it does not just sit in space-time, it reaches out and twists the space around it. The larger the mass and the faster it spins, the stronger the twist. And that twist does not stop at any boundary. It propagates inward, down into the interior of the rotating mass, down past the point where gravity becomes so strong that light itself cannot escape, down toward whatever lies at the center. If the mass collapses into a black hole, the twist collapses with it. And at the center of a rotating black hole, Kerr's mathematics showed, the twist becomes so severe that it reshapes the singularity itself. This is what was waiting for Roy Kerr in his equations. This is what sent Achilles Papapetrou to his feet in that Dallas conference room. The center of a rotating black hole is not a point. It is not a place where space and time simply end, crushed into zero volume. It is something far stranger, and to see it, we must first go back to the beginning, to the first exact solution, derived under circumstances so unlikely they seem borrowed from fiction. In early 1915, the armies of Imperial Germany were bogged down in a war that had already killed more men than any conflict in European history. On the Eastern Front, along a frozen line stretching from the Baltic Sea to the Carpathian Mountains, soldiers lived in conditions of misery that defied description. Flooded trenches, inadequate rations, temperatures plunging below zero, the constant percussion of artillery that could kill you at a distance of several kilometres without warning. Among the soldiers was a 42-year-old astronomer named Karl Schwarzschild. Schwarzschild was not a typical soldier. He was the director of the Potsdam Astrophysical Observatory, one of the most distinguished scientific positions in the German Empire. He had made foundational contributions to stellar photography, photometry, and the physics of the solar atmosphere. At the outbreak of war in August 1914, he was 51 years old, well past conscription age. But he had volunteered for military service anyway, out of a sense of patriotism that was common among the German academic elite of his generation. Now, in the winter of 1915, he was stationed somewhere on the Russian front, helping to calculate artillery trajectories and manage logistical operations. It was brutal, thankless work. The trenches stank of mud and decay. Disease moved through the ranks like a second enemy. The intellectual life Schwarzschild had known, observatories, academic journals, the slow and careful refinement of understanding, had been replaced by the industrialized production of death. But Schwarzschild had brought his mind with him to the trenches, and in the rare quiet moments, by lantern light in a dugout perhaps, or in the pre-dawn hours before an artillery barrage, he continued to work. He had been following, from a distance, the developments in theoretical physics emanating from Berlin. His colleague Albert Einstein, with whom he had corresponded for years, had just completed a decade-long quest to generalize his theory of relativity. The new theory, general relativity, described gravity not as Newton had described it, as a force reaching invisibly across space, but as geometry itself. Massive objects curved spacetime. The paths of light and matter through that curved spacetime were what we experienced as gravitational motion. Einstein had published the field equations of general relativity in late November 1915. They were beautiful, but they were also ferociously difficult. The equations were nonlinear, which meant that solutions could not simply be added together the way solutions to simpler equations could be. Finding any exact solution, any explicit mathematical description of the spacetime geometry around a given configuration of matter would require extraordinary ingenuity. On the 22nd of December 1915, Karl Schwarzschild mailed a letter from the Eastern Front to Albert Einstein in Berlin. Inside the letter was a manuscript. In it, Schwarzschild announced that he had done what Einstein himself had not yet managed. He had found an exact solution to the field equations. It was the solution for the gravitational field around a perfectly spherical, perfectly static, non-rotating mass. An idealized object like a frozen star, not spinning, simply sitting in space and warping the geometry around it. Schwarzschild had derived the precise mathematical form of that warping. Einstein received the letter in Berlin. His response, dated December 29th, was generous and astonished. He wrote to Schwarzschild that he had not expected anyone to find an exact solution so quickly, perhaps not for years. The solution was elegant. It was illuminating. It would become the cornerstone of all future work in the physics of gravity. Schwarzschild's paper was published in January of 1916, less than 2 months after Einstein's own equations had first appeared. But there was something troubling in the mathematics. Schwarzschild had noticed that his solution contained a peculiar feature. If you imagined compressing all of the mass into a smaller and smaller region, squeezing it past the point where light could no longer escape, past what we would now call the event horizon, then the equations predicted that at the very centre something catastrophic would occur. The curvature of space-time would become infinite. The density would become infinite. Every mathematical quantity that described the geometry of the region would diverge, would shoot off toward infinity, would cease to be meaningful. At the exact centre, there would be a point, a single point, dimensionless, with no volume at all, where the structure of space-time simply ceased to exist in any recognizable form. This was the singularity. In Schwarzschild's solution, the singularity was a point, a geometric full stop, a place where physics ended, where the equations broke down, where the entire mathematical framework that described gravity and matter and space and time gave up and returned a value of undefined. For decades, physicists debated what this meant. Some argued that singularities were physically impossible, that the mathematics was simply failing to capture some crucial piece of physics that would prevent real matter from ever reaching such a state. Others argued that singularities were real, but that they were safely hidden behind event horizons, invisible to the outside universe, unable to influence anything beyond their gravitational pull. Still, others tried not to think about singularities at all. But throughout these decades, one assumption remained constant. If a singularity existed, it was a point, 0 dimensions, no structure, no interior, no way through. The Schwarzschild solution described the simplest possible black hole, one that did not rotate, one that had no angular momentum, one that sat perfectly still while the universe swirled around it. And in the Schwarzschild solution, the singularity was the ultimate prison. Everything that fell past the event horizon was doomed to reach the singularity. There was no escape, no exit, no passage to anywhere else. The singularity was the end of the road, full stop. This was the picture of black holes that physics carried for nearly 50 years. It was the picture that Roy Kerr shattered. The problem, of course, was that the Schwarzschild black hole did not exist, not in nature, not in any realistic astrophysical scenario, because the Schwarzschild solution required something that the universe does not provide, a massive object that does not rotate. Think about what rotation means for a collapsing star. Before the collapse, the star is spinning. Slowly perhaps, but spinning nonetheless. Every main sequence star rotates, because rotation is a relic of the original angular momentum of the gas cloud from which the star formed, and angular momentum, unlike so many other quantities, is conserved. It does not disappear. It does not leak away. If you begin with rotation, you end with rotation. When a massive star exhausts its nuclear fuel and begins its final collapse, when gravity overwhelms the internal pressures that had held the star in equilibrium, and the core begins to fall inward, compressing itself toward densities that would have been unimaginable to pre-20th century physics, the rotation does not stop. It cannot stop. If anything, it accelerates. Picture an ice skater pulling her arms in during a spin. As her mass moves closer to the axis of rotation, she spins faster. This is conservation of angular momentum in its most visceral form. The same principle applies to a collapsing star. As the mass falls inward, as the radius shrinks by factors of thousands and millions, the rotation rate increases correspondingly. A star that rotated once every 25 days, like our Sun, might, if it were massive enough to collapse into a black hole, end up with a rotation rate measured in milliseconds. And so the black holes that actually form in the universe, from collapsing massive stars, from the mergers of neutron stars, from the primordial collapses in the early universe that may have seeded the supermassive monsters at the centers of galaxies, are rotating. All of them, every last one. A Schwarzschild black hole, perfectly static, perfectly still, is a mathematical idealization that has never existed and will never exist. This was the problem that haunted relativists for decades. Einstein's equations had been solved exactly for a non-rotating mass. That solution was elegant, profound, and physically unrealistic. The equations had not been solved, not exactly, for a rotating mass. There were approximations, there were perturbative approaches, which assumed the rotation was slow and treated it as a small correction to the Schwarzschild geometry. There were numerical methods, which traded elegance for brute computational force. But an exact solution, a closed-form mathematical description of the spacetime around an arbitrary rotating mass, remained elusive, and then Roy Kerr found it. Kerr was working at the University of Texas at Austin in the academic year of 1962 to 1963. He had come to the United States from New Zealand, born in Kurov, educated in Christchurch at the University of Canterbury, where he had received his doctorate, and had spent time at Cambridge before landing in Austin. He was young, even by the standards of a discipline that had always favoured young minds. He was steeped in a particular branch of mathematical physics that sought exact solutions to Einstein's equations by hunting for algebraic symmetries, special classes of solutions whose structure was constrained enough to make the nonlinear chaos of the field equations tractable. Kerr had been thinking about algebraically special metrics. This was the technical term for a particular class of solutions to Einstein's equations, solutions in which certain combinations of the curvature tensor took on simplified forms, solutions that had extra symmetry beyond the obvious. The hope was that by restricting attention to this special class, one might find solutions that would be impossible to discover by more general methods. He was exploring an ansatz, a particular mathematical guess about the form the solution might take. He tried one combination of variables, he tried another. He manipulated tensor equations with the grinding patience that characterized exact work in general relativity, where a single sign error could waste weeks of labor. And then, in May of 1963, something closed. The equations balanced. The ansatz worked. Kerr had found an exact solution to Einstein's field equations for a rotating mass. He wrote it up in 2 pages. 2 pages. The paper that would reshape the entire field of black hole physics was shorter than the instruction manual for most household appliances. The title was bland, almost deliberately obscure. Gravitational field of a spinning mass as an example of algebraically special metrics. The abstract was technical. Nothing about the paper announced that it contained a revolution. It was published in the Physical Review Letters on the 1st of September 1963, and at first, almost no one noticed. That was the state of affairs when Kerr arrived in Dallas in December of that year, when he was allotted his 10 minutes at the Texas Symposium on Relativistic Astrophysics, when the audience began to doze, when Achilles Papapetrou rose to his feet and changed the tenor of the entire conference. Kerr's solution, the Kerr metric as it would come to be called, described the spacetime geometry around a rotating mass with 2 parameters, the mass itself and the angular momentum. It reduced to the Schwarzschild solution when the angular momentum was set to 0. But when the angular momentum was non-zero, the geometry changed in ways that were not merely quantitative but structural. The singularity was no longer a point. In the Schwarzschild solution, you could approach the center along any radial direction, and you would hit the singularity, that dimensionless point of infinite density, at the same location, regardless of your angle of approach. In the Kerr solution, this was not true. The singularity in a rotating black hole was not a point, it was a ring, a one-dimensional ring, lying in the equatorial plane of the rotation, with a radius that depended on the spin parameter. If you approach the center from directly above the pole, moving straight down along the axis of rotation, you would not hit the singularity at all. You would pass through the center of the ring, through the eye of the needle, and emerge on the other side. And on the other side, according to the mathematics, was something that should not exist. Another space-time, another universe, asymptotically flat, which is to say, looking more and more like ordinary empty space as you moved farther from the ring. A region that was not simply a continuation of the original space-time, but a geometrically distinct extension, joined to the original only through the interior of the rotating black hole, accessible only by passing through the ring. This was what Chandrasekhar meant years later when he called his encounter with the Kerr metric the most shattering experience of his scientific life. Subrahmanyan Chandrasekhar, the Nobel laureate, the astrophysicist who had calculated the limiting mass of white dwarfs before Kerr was born, looked at the Kerr solution and realized that it described untold numbers of massive black holes that populate the universe. Untold numbers, because every real black hole spins, and every spinning black hole, according to Kerr's mathematics, does not end in a wall, it ends in a doorway. The universe had always been larger than we thought. Now, suddenly it seemed that it might be infinitely larger, that behind every rotating black hole there might be another universe, and behind every rotating black hole in that universe, another universe still, and so on, without limit, without end. This was what the mathematics said. This was the structure Kerr had uncovered with his 2-page paper. And in the 6 decades since, physics has not fully recovered. The night after Papapetrou's intervention, in the hallways and hotel bars of the Statler Hilton, a new kind of conversation began. Relativists who had spent their careers on the Schwarzschild solution now had something new to study. The Kerr metric was not just another solution, it was the solution that mattered, the one that actually described the black holes that formed from real astrophysical collapses. If you wanted to understand what happened at the center of a quasar, what lay at the heart of a collapsing massive star, what the universe was really made of in its most extreme configurations, you had to understand Kerr. And understanding Kerr meant grappling with the ring. The ring singularity was not like the point singularity of Schwarzschild. It had structure. It had extent. It was one-dimensional, yes, infinitely thin in every direction perpendicular to itself, but it traced out a circle in the equatorial plane, and that circle had a radius, and that radius depended on how fast the black hole was spinning, and through the centre of that circle, through the hole in the ring, the mathematics allowed trajectories that did not end. Time-like trajectories, which is to say, trajectories that could be followed by a particle with mass, trajectories that could in principle be followed by a spacecraft or a person. This was not an abstraction. This was not a mathematical curiosity that only appeared in limiting cases or required unphysical assumptions. This was a structural feature of the exact solution for a rotating mass. Every rotating black hole, according to the Kerr metric, contains a passage, and on the other side of that passage the mathematics continues. The equations do not break down, the spacetime does not end. There is more universe, or at least more spacetime, waiting. Kerr himself was careful not to overclaim. He was a mathematician by training, and he understood the difference between a mathematical solution and a physical prediction. Just because the equations allowed something did not mean nature would permit it, but the solution was exact. The solution was there, and the structure it revealed, the ring, the passage, the asymptotically flat regions on the other side, was a feature of the mathematics itself, not an artifact of approximation. What did it mean? That question has haunted physics for 60 years. It has spawned research programs and doctoral dissertations, conferences and controversies. It has inspired science fiction that sometimes captures the mathematics and sometimes distorts it beyond recognition. And it has led eventually to a debate that remains unresolved. Whether the singularity itself, point or ring, must form at all, or whether it is, as Roy Kerr would argue decades later, a mathematical mirage that nature never permits. But to understand that debate, we must first go deeper. We must follow the mathematics further into the black hole's interior. We must learn to read the maps that physicists have drawn of these impossible geometries, maps called Penrose diagrams, where infinity fits on a page and the stacking of universes becomes visible at a glance. We must see the ladder for ourselves, and we must confront the final horror, the one that even science fiction rarely dares to name. Because through the ring singularity, if you take the right path, you can reach the past, your own past. You can loop back on yourself, meet yourself, contradict yourself. The Kerr metric does not just permit travel to other universes, it permits closed time-like curves. It permits, in principle, the violation of causality itself. This is what was hiding in Roy Kerr's 2-page paper. This is what Achilles Papapetrou sensed when he rose to his feet in Dallas, when he told the dozing audience to pay attention. The floor of the universe had cracked open, and through the crack something was visible that no one had expected to see. A corridor through the centre of a spinning black hole, a passage to somewhere else, and perhaps, if the mathematics can be trusted, a path that loops back to the beginning, the ring that replaced the point. To understand what Kerr found, we must return to the mathematics, not to drown in formalism, but to extract the single image that will stay with us through everything that follows. The Schwarzschild solution, that elegant description of a non-rotating mass, placed its singularity at a point, a dimensionless point, the way we learned in school. No length, no width, no depth. Everything that fell into a Schwarzschild black hole would be drawn inexorably toward that point, crushed into it, ended by it. The singularity was where the story stopped, but Kerr's solution contained something different. When you write down the metric for a rotating mass, when you account for the angular momentum that any real collapsing star must carry, the singularity changes shape. It stretches, it opens. What was a dot becomes a loop. Picture it this way. In the coordinates that physicists use to describe the Kerr geometry, Boyer-Lindquist coordinates, named after the researchers who developed this particular way of charting the black hole's interior, there is a quantity called S, the Greek letter sigma. Sigma depends on where you are in the spacetime. It depends on your radial coordinate, which physicists call r, and on your angular position relative to the equator, which they call theta. The formula is not difficult. Sigma equals r squared plus a squared times the cosine squared of theta, where a is the spin parameter, the measure of how fast the black hole rotates, defined as the angular momentum divided by the mass, J/m, a number that can range from 0 for a black hole that doesn't spin at all, up to a maximum value equal to the mass itself for a black hole spinning as fast as physics allows. Now here is the crucial point: the singularity, the place where the gravitational field becomes infinite, where the curvature of space-time diverges, where the mathematics screams that something has gone terribly wrong, occurs where sigma equals 0, not where r equals 0, not at a single central point, but where sigma vanishes. And sigma vanishes only when two conditions are simultaneously met. First, r must equal 0, but that is not enough. Second, the cosine of theta must also equal 0, which means theta must equal 90 degrees, the equatorial plane. Sigma is 0 only at r equals 0 and theta equals p/2. What does this describe? Not a point. A point would be a single location in space, a dot with no extent. This is different. At r equals 0 and theta equals 90 degrees, you're everywhere on a circle. You're on a ring of radius a, the spin parameter, lying flat in the equatorial plane. That ring is where sigma vanishes. That ring is where the singularity lives. The ring has no thickness. It is one-dimensional, a closed curve, a loop. If you approached it from above or below, from the poles of the black hole's rotation, you would not encounter the singularity at all. The singularity is not in front of you. It is off to the side, at the equator, and if you approached it along the equatorial plane itself, you would find that the singularity is not a wall or a barrier. It is a ring, and rings have holes in their centres. This is not a metaphor. This is not a poetic description designed to make the mathematics more accessible. This is what the mathematics says. Roy Kerr's solution, published in September of 1963 in Physical Review Letters, replaces the point singularity of non-rotating black holes with a one-dimensional ring-shaped gravitational singularity. The curvature invariants, the mathematical quantities that describe how sharply spacetime is curved, quantities that cannot be eliminated by choosing clever coordinates, diverge along this ring. They go to infinity there. Physics, as we understand it, ends there, but only there, not at a point, at a loop. Let that image settle. At the centre of every spinning black hole formed from a rotating star, every black hole that accretes matter with angular momentum, every black hole that nature actually produces, there is not a dot but a circle, a ring of infinite curvature, infinitely thin but extended, a ring with a hole in its centre. What is in that hole? The corridor through the ring. Here is where the Kerr solution becomes something more than a mathematical curiosity. Here is where it becomes, depending on your philosophical disposition, either the most exciting or the most disturbing prediction in all of general relativity. In the Schwarzschild geometry, the point singularity is a destination. Every path inside the event horizon leads to it. Once you cross the Schwarzschild radius, once you fall past the point of no return, your future contains the singularity and nothing else. The radial coordinate r, which outside the black hole describes your distance from the centre, becomes inside the black hole something more like a measure of time, and that time runs out at r equals 0 at the point, at the singularity. You cannot avoid it. You cannot miss it. It is not somewhere in space that you might manage to steer around. It is somewhere in your future, and you are falling toward it the way we are all falling toward tomorrow. But the ring singularity of the Kerr geometry is different, because it has shape, because it has extent, because it is located at a specific place on the equatorial plane at r equals 0, but only at theta equals 90 degrees, rather than being the inevitable endpoint of all possible futures. The ring singularity can be missed. Think about what that means. Imagine a particle falling into a rotating black hole. Imagine it approaching the centre, passing through the outer event horizon, then through the inner horizon, because rotating black holes have two, descending into the deep interior where the geometry twists in ways that challenge visualization. As this particle approaches r equals 0, as it nears what corresponds to the centre, what happens? If the particle is on the equatorial plane, if theta equals 90 degrees, then as r approaches 0, the particle approaches the ring singularity itself. The tidal forces become unbounded, the curvature diverges, the particle is destroyed, torn apart, ended. The story stops. But if the particle is not on the equatorial plane, if it approaches r equals 0 at some other angle, from slightly above or slightly below the equator, then something else happens. The particle approaches the ring, yes, but it does not approach the singularity, because the singularity is only on the ring itself. The particle can pass through the plane defined by the ring, through the hole in the centre, without ever touching the one-dimensional curve where the curvature diverges. This is what the mathematics shows. Geodesics, the paths that freely falling particles naturally follow, the straightest possible lines through curved space-time, can thread through the ring's interior. They can approach r equals 0, pass through, and emerge on the other side. The singularity has a hole in it, and that hole is traversable. What is on the other side? This is where the Kerr solution becomes genuinely strange. On the other side of the ring, r becomes negative. Pause on that for a moment. In ordinary space, in flat space-time, in Newtonian physics, in everything we learned about coordinates in school, radial distance is always positive. You cannot be at a negative distance from the centre of something. The concept does not pass. Distance is a magnitude, and magnitudes are non-negative by definition. But the Kerr geometry is not ordinary space. The coordinate r in Boyer-Lindquist coordinates is not quite the same thing as distance in the intuitive sense. It is a mathematical label, a coordinate, and coordinates can take on any values that the mathematics allows. In the Schwarzschild geometry, r is always positive and goes to 0 at the singularity. But in the Kerr geometry, r can pass through 0, through the ring, and continue to negative values. What does negative r mean? What kind of space has negative radial coordinate? The mathematics calls it another asymptotically flat region. Asymptotically flat is the technical term for spacetime that, far from any gravitating mass, looks like the ordinary flat spacetime of special relativity. The universe we live in, far from any stars or black holes, is asymptotically flat. Straight lines are straight. Triangles have angles that sum to 180 degrees. Light travels in paths we can predict with simple geometry. The region with positive r, outside the black hole, is asymptotically flat. That is our universe. Or at least it is a mathematical representation of our universe. But the mathematics says there is another asymptotically flat region on the other side of the ring, in the domain of negative r, and that region is, in a very precise mathematical sense, a separate universe. This requires careful qualification. The word universe carries baggage. It suggests stars and galaxies, matter and energy, history and evolution. The mathematics does not promise any of that. What it promises is space-time, a manifold, a geometric structure, a place where particles could move and clocks could tick. Whether that space-time contains anything, whether it has its own stars and planets, whether it has any physical reality at all, is a question the mathematics does not answer. But the mathematics does answer one question definitively. The two asymptotically flat regions are connected. Null geodesics, the paths of light rays, can traverse from the positive or exterior, through both horizons, through the ring singularity, and emerge into the negative or region. The connection is real, in the sense that the equations describe it. It is not a gap or a discontinuity. It is a passage, and the passage can be travelled by material objects, not just by light, which travels on null geodesics, but by massive particles, which travel on time-like geodesics. The Kerr geometry contains time-like paths, paths that observers with mass could follow, paths that clocks could tick along, that thread through the centre of the ring and emerge on the other side. These are not paths that require infinite energy or impossible accelerations. They are natural geodesics, the paths of free fall. This is what separates the Kerr ring singularity from the Schwarzschild point. The point singularity is a terminus, a dead end, the end of the road. The ring singularity is a gateway. The mathematics permits through travel, but the mathematics also contains warnings. Geodesics approaching the ring, singularity experience tidal stresses that grow without bound. Even paths that thread through the centre, that never touch the ring itself, pass close to a region of infinite curvature. The tidal forces, the stretching and squeezing that any extended object feels in a gravitational field, become arbitrarily large near the ring. An observer falling through might survive mathematically, in the sense that their world line continues, but physically, any material object would be subjected to forces beyond imagination. How close is too close? The mathematics does not draw a clear line. The ring itself is infinitely thin, one-dimensional, so in principle you can pass arbitrarily close to it without touching. But the tidal forces grow as you approach. For a small enough object, for a trajectory that threads precisely through the centre, survival might be possible. For anything large, for any path that comes too close, destruction seems assured. And there is another question, one that haunts all discussions of black hole interiors. Can we trust the mathematics this far? Roy Kerr's solution is exact. It is not an approximation or a limiting case. It satisfies Einstein's field equations precisely, with no error terms, no neglected contributions. In that sense, the mathematics is unimpeachable. The ring singularity is there, the passage through the ring is there, the negative R region is there. These are features of the solution itself. But a mathematical solution and a physical reality are not the same thing. The Kerr metric describes the space-time outside and inside a rotating mass, but it describes an idealized, eternal vacuum solution. The Kerr black hole of the mathematics has always existed and will always exist. It formed in the infinite past and persists forever. This is manifestly not how real black holes form. Real black holes form from collapsing matter, from dying stars, from accumulating gas, from violent mergers. The collapse process is messy, dynamic, non-ideal. Does the passage through the ring survive the collapse? Does the negative R region come into being when a star collapses? Or is it only a feature of the eternal mathematical solution? These are questions that the Kerr metric alone cannot answer. And there is one more concern, a concern that would occupy physicists for decades after Kerr's discovery, a concern that remains controversial to this day. The inner regions of the Kerr geometry, the regions near the ring singularity, are classically unstable. Small perturbations, the faintest whisper of additional matter or radiation falling in, might fundamentally change the geometry. The carefully constructed passage through the ring might slam shut, or become something else entirely, something not described by Kerr's idealized solution. We will return to these concerns. They are not minor technical objections, but fundamental challenges to the physical reality of the Kerr interior. The Cauchy horizon problem, as it is sometimes called, suggests that the inner regions of rotating black holes might be far more chaotic than Kerr's clean mathematics implies. But for now, in this moment, let us hold on to what the mathematics shows us. A ring, not a point. A loop with a hole in its centre. Geodesics that thread through without touching. A passage to a region of negative R. Another asymptotically flat spacetime. Another universe in the minimal mathematical sense. And time-like paths. Paths that observers with mass could follow, connecting our universe to that other place. This is what was hiding in Roy Kerr's 2-page paper. Not just a better description of rotating masses, not just a more realistic model of astrophysical black holes, but a door. A mathematical door built into the structure of space-time itself, opening onto what? That is the question that has driven 60 years of research. And to even begin to answer it, we need new tools. We need a way to visualize these geometries that the human mind was never evolved to comprehend. We need maps. The physicists who came after Kerr developed such maps. They are called Penrose diagrams, after the British mathematician and physicist Roger Penrose, who pioneered their use. These diagrams take the infinite expanses of space-time and compress them, fold them, arrange them on a finite page so that the causal structure, who can signal whom, which events can influence which other events, becomes visible at a glance. On a Penrose diagram, light rays travel at 45-degree angles. Infinity itself is drawn as a boundary you can see, and the stacking of universes, the ladder of asymptotically flat regions connected by ring singularities, becomes a pattern you can trace with your finger. We will learn to read these diagrams. We will see the ladder for ourselves. But first, we must sit with the image that this section has delivered. A ring, one-dimensional, infinitely thin, lying in the equatorial plane of every spinning black hole, marking the boundary where physics as we know it ends, but only along that curve, only at that loop. Through the centre of the ring, the mathematics continues. Through the centre of the ring, there is more. Roy Kerr found this structure in 1963, writing in the compressed mathematical notation of a Physical Review Letters submission, just 2 pages long. He could not have known, could not have imagined, everything that would follow from those pages. He was solving equations, finding an exact solution that had eluded other researchers, doing the work of a mathematician grappling with the differential geometry of rotating masses. But what he found was a ring that replaced a point, and in replacing it, opened a corridor to somewhere else. The corridor is narrow, the corridor is treacherous. The tidal forces near the ring would destroy anything we know how to build. And whether the corridor even exists in physical black holes, as opposed to idealized mathematical ones, remains an open question. A question that Roy Kerr himself would address directly in a paper published 6 decades later. But the corridor is there, in the mathematics. It has been there since 1963. It will remain there as long as Einstein's equations remain our best description of gravity. And it points toward possibilities that, even now, we do not fully understand. Through the ring, into the region of negative R. Out the other side into an asymptotically flat space-time that is not our universe, or at least not the part of our universe we started from. What waits there? What is the negative R region like? And how many such regions does the full Kerr geometry contain? The answers require those maps, the Penrose diagrams, the visualizations that compress infinity and reveal structure. When we learn to read them, we will see that the Kerr geometry does not contain just one other universe, just one negative R region. It contains infinitely many, a ladder of universes stacked one upon another, connected by rings and horizons in a pattern that repeats forever. And somewhere in that infinite structure, curving back on itself in ways that violate every intuition we have about time and causality, there are paths that return to their own beginnings. But those horrors are for later. For now, we have the ring. We have the corridor. We have the first glimpse of what Roy Kerr's mathematics was trying to tell us about the centers of spinning black holes. Not an end. A passage. Not a point where everything stops. A ring where something begins. And so we come to the maps. Roger Penrose was 31 years old in 1962, already establishing himself as one of the most geometrically gifted minds of his generation. While other physicists worked in coordinates and components, Penrose thought in shapes. He saw mathematics not as a language of symbols, but as a language of form, of structure, of relationships that could be grasped visually if only one knew how to look. And he was frustrated by a fundamental problem in general relativity. The universes described by Einstein's equations were infinite. They stretched outward forever in space, backward and forward forever in time, and no piece of paper, no blackboard, no diagram could capture their entirety. You could draw a portion of a space-time, a patch, a neighbourhood, but the important features, the horizons and singularities, and the fate of light rays travelling for eternity always lay somewhere off the edge of the page. Penrose's solution, developed over several years and formalised in 1963, was elegant in the way that only a geometer's solution can be. He employed a technique called conformal compactification, a method of squeezing infinity itself into a finite region while preserving the one feature that mattered most, the structure of light cones. In Einstein's relativity, the speed of light is the ultimate speed limit. It determines which events can influence which other events. If I shine a flashlight at you, the light travels outward at 300,000 kilometers per second, and only events within that expanding sphere of light can be affected by my action. This causal structure, the web of possible influences threading through space-time, is the skeleton of reality. Penrose found a way to draw that skeleton on a single page. The trick is a coordinate transformation, a mathematical remapping of space-time that brings infinity to a finite distance, while keeping all light rays travelling at the same angle. On a Penrose diagram, light always moves at 45 degrees from vertical. Always. This is not an approximation or a convenient fiction. It is a defining feature of the representation. If you want to know whether one event can send a signal to another, you draw a line between them. If that line tilts less than 45 degrees from vertical, closer to straight up and down, then the signal would need to travel slower than light, which is permitted. A material object, a spaceship, a person could make that journey. If the line tilts exactly 45 degrees, the signal travels at light speed, and if it tilts more than 45 degrees, beyond the light cone, then no signal, no influence, no causal connection is possible. The events are separated by what physicists call a space-like interval. They cannot touch each other. They exist from each other's perspective in an eternal now that can never become a then. This is what Penrose gave us, a way to see causality, a way to draw the entire infinite history of a universe on a finite diagram, and to trace with a finger or a pencil exactly which events can influence which others. The diagrams are more properly called Penrose-Carter diagrams, acknowledging the essential contributions of Brandon Carter, the Australian-born physicist who extended their use to spacetimes more complex than the simplest cases. Carter would become one of the leading figures in black hole physics, and his application of Penrose's conformal techniques to the Kerr metric would reveal structures that Penrose's original diagrams of simpler spacetimes could not have anticipated. But we are getting ahead of ourselves. First, we must learn to read the simplest map before we can comprehend the more complex one. Consider then the Penrose diagram of a Schwarzschild black hole. This is the non-rotating case, the spherically symmetric solution that Carl Schwarzschild found in 1916, the solution with the point singularity at its centre. On a Penrose diagram, the entire eternal Schwarzschild spacetime takes a particular shape. Imagine a square, or more precisely a diamond, turned on its side with corners pointing up, down, left and right. The right corner of the diamond represents future infinity, the distant future of the external universe, where light rays travel forever outward and never encounter anything. The left corner represents past infinity, the beginning of time, the distant past from which light rays have been travelling since forever. The top corner of the diamond, and this is critical, represents the singularity. And the bottom corner represents another region, a mirror image of the external universe that exists only in the mathematics of the fully extended solution. But focus on the essential feature. In the Schwarzschild diagram, the singularity is not a point in the centre of the space. It is a line at the top of the diagram, a horizontal line, a boundary. And this boundary is space-like. It tilts more than 45 degrees from vertical. In fact, it is perfectly horizontal, which means that once you cross the event horizon, once you enter the black hole, the singularity is not in front of you in space. It is in front of you in time. It is your future, and you cannot avoid your future any more than you can avoid next Tuesday. You will reach the singularity not because you travel toward it, but because time itself carries you there. Every path, every trajectory, every desperate maneuver you might attempt within the event horizon leads to the same destination, that horizontal line at the top of the diagram, that lethal edge, the place where space-time ends. This is what the Penrose diagram of a Schwarzschild black hole teaches us. The event horizon is a point of no return not because the gravity is too strong to escape, though it is, but because the geometry of space-time has been so warped that the singularity has become a moment in time rather than a place in space. You fall into a Schwarzschild black hole the way you fall into tomorrow, inevitably, inexorably, without possibility of reversal. The diagram makes this visible. The causal structure is laid bare. Every 45-degree line you draw from any point inside the horizon, tracing the path of a light ray, or the fastest possible trajectory of a spacecraft, tilts upward and intersects that top edge. There is no escape because escape would require tilting beyond 45 degrees. It would require travelling faster than light. It would require violating the most fundamental speed limit in the universe. So the Schwarzschild diagram is, in a sense, a map of a prison with no walls, only geometry. A prison where the bars are made of causality itself. You can see the outside universe from within. Light from the stars still reaches you, falling in alongside you, but you cannot send any signal back. And ahead of you, always ahead of you, is the end. Now, set that image aside, hold it in memory, because we are about to see what Roy Kerr's mathematics does to this picture. The Penrose diagram of a Kerr black hole, a rotating black hole. A black hole with angular momentum is not a square. It is not a diamond. It is not any finite shape at all. It is a ladder, an infinite ladder, extending upward and downward without end. A stack of regions connected at their throats, linked by horizons and ring singularities in a pattern that repeats forever. where the Schwarzschild diagram shows you a universe falling into an inescapable endpoint. The Kerr diagram shows you universes plural, an infinite succession of them, and paths that thread through the stack from one to the next. The difference is the ring. Remember, in the Schwarzschild geometry, the singularity is a point, and that point becomes, on the Penrose diagram, a horizontal line at the top of the figure, a space-like boundary that everything inside the horizon must eventually strike. But in the Kerr geometry, the singularity is a ring. It lies in the equatorial plane. It can be avoided. Trajectories that pass through the centre of the ring do not encounter infinite curvature. They continue. And on the Penrose diagram, this changes everything. The ring singularity appears not as a horizontal boundary blocking all futures, but as a vertical feature. It is time-like. It can be avoided. And beyond it, through it, lies the negative region we have already encountered. The region where r, the radial coordinate, takes values less than 0. The region where the mathematics continues, strange and unfamiliar, describing a spacetime that is not our spacetime but that connects to ours through the throat of the ring. On the Penrose diagram, this negative r region appears above the ring singularity. It is a distinct zone, a separate patch of the diagram, representing a piece of spacetime where things are different. And above that region, connected to it by another horizon, another transition in the causal structure, lies another asymptotically flat region, another external universe, a place where, far from the black hole, spacetime becomes flat and ordinary, where an astronomer looking up at the night sky would see stars and galaxies, would measure the same laws of physics, would have no immediate reason to suspect that her universe is not the universe, that it is in fact one rung up a cosmic ladder, one level removed from the universe where we began, and the ladder continues. Below the ring singularity of our original universe lies another external region, a white hole in the language of the fully extended solution, the time reverse of a black hole, and below that another ring singularity and another negative region, and another asymptotically flat universe descending forever. Above our universe, through the black hole, past the ring, through the negative r region, the pattern repeats ascending forever. This is not a metaphor. This is not a science fiction conceit. This is what the mathematics says. The maximally extended Penrose diagram of a Kerr spacetime is infinite in extent, and it contains infinitely many distinct asymptotically flat regions, each of which, to an observer living within it, would appear to be a complete universe unto itself. Brandon Carter was among the first to fully map this structure, to draw the Penrose diagrams that revealed the ladder in all its infinite extent. When he applied Penrose's conformal techniques to the Kerr metric in the 1960s, the diagrams that emerged were unlike anything general relativity had produced before. They showed not a universe with a black hole in it, but a multiverse connected by black holes, a network of causally linked regions, some accessible from others, some forever separated, with the ring singularity serving as a gateway between rungs of the ladder. What does asymptotically flat mean in concrete terms? It means that far from the centre of the geometry, far from the black hole, far from the ring singularity, spacetime becomes indistinguishable from the ordinary flat spacetime of special relativity. Gravity weakens with distance, curvature diminishes, and at infinite remove, the geometry is the geometry of empty space, the geometry of a universe without gravity, the geometry where straight lines remain straight and parallel lines never meet. This is what our universe looks like, far from any mass. This is what the other universes in the Kerr ladder look like, far from their respective connections to the ladder. To an observer in any one of them, looking out at the cosmos from a position far from the black hole, the universe would appear complete, closed, self-contained. The stars would shine, gravity would follow the inverse square law, physics would work as physics works, but the observer would be wrong about the completeness. Somewhere in her universe, if she could find it, there would be a rotating black hole, and through that black hole, through its ring singularity, through the strange negative region beyond, there would be a passage to another universe, and from that universe, through another black hole, another passage, and so on in both directions forever. Roy Kerr proposed in later work that the singular ring must be replaced by an actual rotating body, such as a neutron star, to construct a physical solution. In this view, the central ring and the second sheet of spacetime would disappear, and the metric would become non-singular. The mathematical structure of the infinite ladder would be an artifact of the idealized eternal solution, not a feature of real astrophysical objects. This remains a matter of debate. The mathematics permits the ladder. Whether nature builds one is another question. But the mathematics permits it. That is the point we must not lose. The equations of general relativity, applied to a rotating mass, produce a geometry in which there is not one universe but infinitely many. Where the passage through a ring singularity leads somewhere, where the word else in somewhere else has a precise technical meaning, another asymptotically flat region, another rung of the ladder, another cosmos. And now we must speak of the horror. Because the negative region, the strange zone that lies beyond the ring singularity, the intermediate territory between one universe and the next, is not merely strange. It is pathological. The mathematics that describes it contains features so disturbing that physicists have debated for 60 years whether they should be taken as predictions of reality or as signs that the theory breaks down, warnings that we have extrapolated beyond the domain where our equations can be trusted. The pathology is this. The negative R region contains closed, time-like curves. A curve, in this context, is simply a path through space-time, a world line, the trajectory of an object as it moves through space and persists through time. And time-like means that the path moves slower than light at every point. It is the kind of path that a material object, a spaceship, a person can follow. All of our lives, all of our histories, are time-like curves. We move from moment to moment, from place to place, carried along our world lines by the flow of time. A closed time-like curve is a path that returns to its starting point. Not in space alone. We do that every time we walk in a circle, but in space-time. A closed time-like curve brings a traveller back to the same location and the same moment. It is a loop in time, a trajectory where the future leads back to the past, where if you follow the path long enough, you arrive at a point in space-time that you have already visited, that you will visit again, that you are visiting now and then and always. In most space-times, closed time-like curves do not exist. The geometry does not permit them. Causality is preserved. Effects follow causes. The past determines the future, and the arrow of time points in one direction. But the Kerr metric in the negative R region is not most spacetimes. The mathematics is precise. In Boyer-Lindquist coordinates, the coordinates most commonly used to describe the Kerr geometry, there is a quantity called g sub phi phi, the component of the metric tensor that describes the geometry in the angular direction, the direction of rotation. In our universe, in the external region far from the black hole, this quantity is positive. It has the sign it should have. Angles work the way angles should work. But in the negative R region, inside the Kilsey horizon, g sub phi phi becomes negative. This sign changes everything. When g sub phi phi is negative, the angular direction, the direction around the ring, the direction of the black hole's rotation, takes on the properties of a time direction. And this means that a path that winds around the ring, a path that would seem to be a path through space, is actually a path through time. And if you wind around far enough, if you follow the path to its end, you return to your beginning. You return to your own past. The closed time-like curves in the Kerr geometry are not hypothetical. They are not a matter of interpretation. They are as much a feature of the solution as the ring singularity itself, as the event horizons, as the frame dragging that we will discuss in later sections. They emerge directly from the equations. If the Kerr metric correctly describes the interior of rotating black holes, then rotating black holes contain regions where causality is violated, where the grandfather paradox, the old thought experiment about travelling back in time and preventing your own birth, is not a paradox but a structural feature of space-time. The closed time-like curves are confined to the region inside the Kilsey horizon. They do not extend into our external universe. A traveller in our cosmos cannot simply fly to a rotating black hole and use it as a time machine without first crossing horizons, traversing the negative region, navigating the catastrophic tidal forces near the ring. But the curves exist in the mathematics. They are there, waiting, in every Kerr solution. This is what disturbs physicists, not merely the singularity, which at least has precedent, Schwarzschild's solution contained a singularity, and we have learned to live with the idea that spacetime can end. Not merely the ring structure, which is strange but not paradoxical. Not even the ladder of universes, which is conceptually challenging but does not violate logic. The closed time-like curves are different. They suggest that general relativity, extrapolated to its logical conclusions, permits the violation of causality itself. And causality, the principle that effects follow causes, that the future is determined by the past, that influence propagates forward in time, is the foundation on which all of physics and all of rational thought is built. If effects can precede causes, then prediction is impossible. If the future can influence the past, then the past is not fixed. If you can meet your own earlier self, then you're not a single continuous being moving through time, but a strange loop, a paradox given flesh, a walking contradiction. Physicists have proposed various ways out of this horror. Some argue that the closed time-like curves are artifacts of the idealized Kerr solution and would not appear in realistic rotating black holes formed by stellar collapse. The mathematics of the eternal Kerr metric is exact, but physical black holes are not eternal. They form from matter, they evolve, they may be perturbed by infalling material. Perhaps the perturbations destroy the Cauchy horizon, prevent the negativa region from forming, close the door on the closed curves before any traveller could reach them. This is related to what physicists call strong cosmic censorship, the hypothesis that nature in some form forbids the pathologies that pure mathematics permits. Others argue that quantum effects, not included in classical general relativity, would modify the geometry at the scales where the closed curves appear. The Kerr metric is a solution of Einstein's classical field equations, which describe gravity at large scales where quantum effects are negligible. Near the ring singularity, where curvatures become extreme, quantum gravity, whatever that theory turns out to be, must take over. Perhaps quantum gravity closes the loops. Perhaps it smooths the singularity. Perhaps the very concept of a closed time-like curve becomes meaningless when space-time itself fluctuates at the Planck scale. And Roy Kerr himself, in a paper published in 2023, 6 decades after his original discovery, argued that the whole question may be moot. Singularities, he proposed, need not form at all. The assumptions that lead from stellar collapse to mathematical singularity are not as ironclad as physicists have believed. Perhaps the interior of a real rotating black hole is not described by the maximally extended Kerr solution. Perhaps the ring singularity is replaced by a rotating neutron star or some other material object. Perhaps the negative R region, with its closed time-like curves and its ladder of universes, is a mathematical artifact, a feature of the idealized solution that has no counterpart in nature. But we are not yet ready to address Kerr's revolt against the orthodoxy. That comes later, in a later section, when we will examine his arguments in detail. For now, we must sit with the horror. We must understand what the mathematics says, even if the mathematics is not the final word. The Kerr metric, published in 1963, describes a space-time geometry containing closed time-like curves, paths that return to their own beginnings, loops in time, and those loops are not tucked away in some exotic regime beyond all conceivable observation. They lie in the negativa region, the region that can be reached, in principle, according to the mathematics, by any traveller who passes through the ring singularity. They are part of the structure, part of the geometry, part of what it means to be a rotating black hole, according to our best theory of gravity. This is not science fiction shorthand. This is not a Hollywood device dressed in equations. This is what the metric says. The sign of G sub phi phi flips. The angular direction becomes time-like, and time-like closed loops become possible. Causality, in the negativa region of a Kerr black hole, is negotiable. We cannot yet say whether this is a prediction or a pathology. We cannot yet say whether nature builds these geometries or forbids them. We cannot say whether anyone will ever traverse the ring, enter the negative R region, and confront the possibility of meeting their own past self. But we can say this: the mathematics permits it. Einstein's equations, Kerr's solution, the geometry of rotating black holes as we understand them, they contain this possibility. It has been there since 1963. It will remain there until we find a theory that supersedes general relativity, or until observations tell us that the Kerr interior is different from what the mathematics describes. The ladder of universes is strange enough. The idea that you could, in principle, travel through a rotating black hole and emerge in another asymptotically flat region, another cosmos, is strange enough. But the ladder is merely strange. The closed time-like curves are something more. They are a challenge to the coherence of our understanding of reality, a challenge that the Kerr metric issued 60 years ago and that remains open today. And so, we find ourselves here, on a rung of the ladder, looking up at the infinite stack of universes above us and down at the infinite stack below, knowing that somewhere in the geometry between the rungs, time loops back on itself. The ring singularity is not just a passage to elsewhere, it is a passage to else-when. The corridor through the centre of the ring leads not only to another universe, but potentially to our own past. This is what Roy Kerr found in those 2 pages published in Physical Review Letters in 1963. This is what follows from the mathematics of rotating masses and curved spacetime. This is what waits in the equations, in the Penrose diagrams, in the structure of every spinning black hole, if the structure is indeed as the equations describe, and every astrophysical black hole spins. Every astrophysical black hole spins. This is not a theoretical preference. It is not an assumption made for mathematical convenience. It is a consequence of how black holes form, and it is confirmed by every observation we have made of these objects in nature. Consider a star, any star. Our Sun, for instance, completes one rotation roughly every 25 days at its equator. The stars that will one day collapse into black holes, massive stars, 8 or 10 or 20 times the mass of the Sun, also rotate. Some rotate slowly. Some rotate with ferocious speed, completing a full turn in mere hours. But all of them rotate. All of them carry angular momentum, that conserved quantity that describes the tendency of a spinning object to keep spinning, unless something acts to slow it down. When a massive star exhausts its nuclear fuel and its core collapses, when the outward pressure of fusion can no longer resist the inward pull of gravity, the core does not simply fall straight down into a point. It cannot. The angular momentum must be conserved. As the radius shrinks, the rotation rate increases, the same principle that makes a figure skater spin faster when she pulls her arms inward. A stellar core that rotated once per day will, as it collapses toward black hole densities, spin up to hundreds or thousands of rotations per second. And when the collapsing matter crosses its own event horizon, and a black hole is born, that angular momentum does not vanish. It becomes encoded in the spacetime geometry itself, the Kerr geometry. There is no mechanism by which a star can shed all of its angular momentum before collapse. There is no process that bleeds away rotation completely. Some angular momentum may be lost in the supernova explosion that often accompanies core collapse. Some may be carried away by ejected material or electromagnetic radiation, but not all of it, never all of it. The black hole that forms inherits whatever angular momentum remains, and that angular momentum shapes the spacetime around it into the rotating geometry that Roy Kerr described. The same logic applies to supermassive black holes, the giants that lurk at the centres of galaxies. These monsters grow by accretion, by swallowing gas, dust, stars, and smaller black holes over billions of years. The material that falls into a supermassive black hole does not fall straight in. It spirals, it forms an accretion disk, a flattened structure orbiting the black hole, and as that material gradually loses energy and crosses the event horizon, it carries its orbital angular momentum with it. Every meal the black hole consumes adds not only mass but spin. Over cosmic time, supermassive black holes are spun up by the cumulative angular momentum of everything they have swallowed. The Schwarzschild solution, Karl Schwarzschild's 1916 metric describing a static, non-rotating mass, is an idealization that has no counterpart in the real universe. It is a useful fiction, a pedagogical starting point, a simplified model for calculations. But no black hole we have ever observed is described by the Schwarzschild metric. Every black hole we have found is described, to the degree we can measure, by the Kerr metric, the geometry with the ring singularity, the geometry with the ergosphere, the geometry with the two horizons, outer and inner. The geometry that permits, in its mathematical interior, closed time-like curves and passages to other asymptotically flat regions. This is not speculation. We have measured it. In 1964, a rocket-borne Geiger counter was launched above Earth's atmosphere to survey the X-ray sky, a region of the electromagnetic spectrum blocked by our planet's air and thus invisible from the ground. Among the sources detected was a bright point in the constellation Cygnus, designated Cygnus X1. The X-rays were too intense to come from an ordinary star. Something extraordinary was happening there. Something involving temperatures of millions of degrees, something requiring an explanation beyond normal stellar physics. Over the following years, astronomers trained optical telescopes on the location. They found a blue supergiant star, HDE 2226868, a massive hot star approximately 20 times the mass of our Sun. But the star was not alone. Spectroscopic observations reveal that HDE 2226868 was wobbling. Its light showed periodic Doppler shifts. Blue shifted as the star moved toward Earth, red shifted as it moved away, completing a cycle every 5.6 days. The star was orbiting something invisible, something massive enough to pull a blue supergiant around like a child swinging a ball on a string. The mass of the unseen companion could be inferred from the orbital dynamics. It was roughly 15 solar masses, far too heavy to be a white dwarf, which cannot exceed about 1.4 solar masses. Far too heavy to be a neutron star, which collapses into a black hole beyond approximately 3 solar masses. The invisible object in Cygnus, the source of those powerful X-rays, had to be a black hole. In 1971, after years of accumulating evidence, Cygnus X1 was officially confirmed as the first black hole ever discovered. The X-rays were produced by gas from the blue supergiant companion spiraling into the black hole, heating to millions of degrees as gravitational potential energy converted to thermal radiation. But the confirmation of its existence was only the beginning. In the decades that followed, astronomers refined their observations. They measured the X-ray spectrum in detail, analysed the flickering of the emission, mapped the behaviour of gas in the inner accretion disk where it plunged toward the event horizon. And from these observations they extracted a quantity that Karl Schwarzschild's solution does not even possess: spin. The spin of a black hole affects the geometry of spacetime around it in measurable ways. The innermost stable circular orbit, the closest distance at which matter can orbit without spiralling in, depends on the spin. For a non-rotating black hole, this orbit lies at 3 times the Schwarzschild radius. For a rapidly rotating black hole, the innermost stable orbit draws much closer, pulled inward by the frame-dragging effect that is unique to rotating spacetimes. By analysing the X-ray emission from the inner accretion disk, astronomers can infer how close the disk extends to the black hole, and from that, they can deduce the spin. For Cygnus X1, the answer came back extreme. The black hole is spinning at more than 97% of the maximum possible rate. Its dimensionless spin parameter, the quantity that physicists denote a star, ranging from 0 for no rotation to 1 for the theoretical maximum, exceeds 0.97. Cygnus X1 is not merely rotating, it is spinning at nearly the fastest rate that physics permits. In 2021, astronomers using the Very Long Baseline Array, a network of radio telescopes spanning from Hawaii to the Virgin Islands, working together as a single instrument thousands of kilometers across, refined the measurements further. The distance to Cygnus X1 was determined to be 2.22 kiloparsecs, about 7,200 light-years. The mass of the black hole was measured at 21.2 solar masses, with an uncertainty of about 2 solar masses. These numbers superseded earlier estimates, making Cygnus X1 significantly more massive than previously thought. But the spin remained extreme. The first black hole ever discovered is a near-maximally spinning Kerr black hole. The geometry that Roy Kerr found in 1963 describes, almost exactly, the structure of this object that lies 7,000 light-years away in the direction of the Northern Cross. The same story repeats itself across the sky. Stellar mass black holes in X-ray binary systems, GRS 19-15 Pleiuson-05, LMC X1, GX 33-4, reveal their spins through the same techniques, and the results consistently show rotation. The spins vary. Some are modest, some approach the maximum, but none are zero. None conform to the Schwarzschild idealization. Every black hole whose spin has been measured is described by the Kerr metric, and then there is M87 star. In April 2019, the Event Horizon Telescope collaboration released an image that had been decades in the making. It showed the supermassive black hole at the centre of Messier 87, a giant elliptical galaxy some 55 million light-years from Earth in the constellation Virgo. The image was a ring of light, emission from hot gas swirling around the black hole, surrounding a dark central region, the shadow of the event horizon itself. It was the first direct visual evidence of a black hole's immediate environment, the first image to show the geometry of spacetime warped so severely that light itself could not escape. M87 star is a monster. Its mass is 6.5 billion times the mass of our Sun. If you placed it at the centre of our solar system, its event horizon would extend beyond the orbit of Neptune, out into the Kuiper belt. It is one of the largest black holes in the nearby universe, grown enormous over billions of years by swallowing gas and stars and smaller galaxies that strayed too close. The Event Horizon Telescope did more than photograph the shadow. By analysing the detailed structure of the emission ring, by studying how the light was bent and Doppler shifted and concentrated by the rotating spacetime, researchers extracted the spin of this behemoth. The observations came from coordinated data gathered in 2017 and 2018 by radio telescopes scattered across the globe, from the South Pole to Chile to Spain to Hawaii, all synchronized to function as a single Earth-sized instrument. The resulting measurement placed M87 star's dimensionless spin parameter at approximately 0.8, not as extreme as Cygnus X1, but still rapid rotation, a supermassive black hole spinning at 80% of the maximum rate, dragging spacetime around it in the relentless vortex of the ergosphere, shaped by a geometry that Roy Kerr wrote down using pencil and paper in 1963. The Kerr metric is not a curiosity. It is the geometry of every black hole in the observable universe. This fact transforms everything that came before from mathematical possibility into physical reality. The ring singularity is not an abstraction. It is the structure inside Cygnus X1, inside M87 star, inside the black holes at the centres of the Milky Way and Andromeda, inside the stellar remnants scattered across billions of galaxies throughout the cosmos. The two horizons, outer and inner, are features of real objects that exist in nature, objects we have photographed and measured and mapped. The ergosphere, where no observer can remain stationary no matter how powerful their rockets, wraps around actual black holes in actual space. And the interior structure that the Penrose diagrams reveal, the ladder of universes, the passages through the ring, the negativa region with its causality violating closed time-like curves, is, according to the mathematics, the interior structure of every spinning black hole in existence, billions upon billions of them, one at the centre of nearly every galaxy, countless stellar mass black holes in orbit around companion stars or drifting alone through interstellar space, all rotating, all described to our best theoretical understanding by the Kerr metric. This is what makes the mathematics so urgent. This is why the ring singularity cannot be dismissed as an exotic thought experiment with no bearing on reality. If the Kerr metric accurately describes the interior of rotating black holes, and we have no evidence that it does not, at least until we approach the singularity itself, then the structures it predicts are structures that exist. The passages through the ring are passages that exist. The closed time-like curves are features of actual space-time geometries that nature has built. But of course, there is a profound difference between the exterior of a black hole and its interior. The exterior we can observe, we can photograph the shadow of M87 star, we can analyse the X-rays from Cygnus X1's accretion disk, we can measure the gravitational waves emitted when two black holes spiral together and merge. All of this information comes from outside the event horizon, from the region of space-time that can still communicate with the rest of the universe. The interior is another matter entirely. Information does not escape from beyond the event horizon. No light, no signal, no message of any kind can travel outward from inside a black hole to tell us what is happening there. The event horizon is not merely a boundary of no return for matter, it is a one-way membrane for information itself. Whatever structure exists inside, whatever happens to the ring singularity, whatever form the Cauchy horizon actually takes, whether the negativa region truly exists or the mathematics breaks down before it can form, none of this can be communicated to external observers. The interior of a black hole is, in the most fundamental sense physics allows, unknowable from outside, and so we are left with mathematics, we are left with the Kerr metric, an exact solution to Einstein's field equations, and with the Penrose diagrams that map its causal structure. We cannot verify these predictions directly. We cannot send a probe through a black hole and receive its transmissions from the other side. The event horizon forbids it. The interior remains hidden behind the ultimate information barrier. But we can ask what the mathematics predicts will happen to an observer who crosses that barrier. We can trace the geodesics, the path through space-time that freely falling objects follow, from the external universe, across the outer horizon, through the interior, and toward the ring. We can calculate what such an observer would experience, what they would see, what forces would act upon them. We can follow them mathematically into the abyss, so let us follow. Imagine a probe, call her the probe, for she will serve as our mathematical surrogate on this journey. She's a small spacecraft, heavily instrumented, falling freely toward a Kerr black hole of 10 solar masses. 10 times the mass of our Sun compressed into a region of space some 60 kilometers across. A sphere no larger than a small city, yet containing an abyss in space-time that extends, according to the geometry, through infinite stacked universes above and below. The probe begins her descent from far away, where space-time is nearly flat and the black hole is merely a distant gravitational influence tugging gently on her trajectory. She has crossed the point of no return in a practical sense. She lacks the fuel to escape the black hole's gravitational pull, but space-time around her still resembles the familiar geometry of ordinary space. Stars are visible in every direction. Her instruments register the passage of time normally. The universe behaves as expected. As she falls closer, the black hole's influence intensifies. Space-time begins to curve more severely. If she looks toward the black hole, she sees a dark region against the background stars, not the shadow itself, but the absence of light from behind the hole, bent and lensed around the event horizon. The accretion disk, if one exists, glows brilliantly, a ring of superheated gas spiraling inward. But the probe's trajectory carries her through regions of relative emptiness, away from the violence of accreting matter. She is falling clean along a carefully chosen path toward the outer horizon, and then she crosses it. The outer event horizon is not a physical surface. There is no membrane to penetrate, no wall to breach, no barrier to push through. It is a mathematical boundary, the surface defined by the condition that outward-directed light rays can no longer escape to infinity. From outside, the horizon appears as the edge of the black region, the point beyond which no light returns. But from the probe's perspective, crossing the horizon involves no local drama whatsoever. This is one of the most counterintuitive features of black hole physics. The event horizon is globally significant. It marks the boundary between regions that can and cannot communicate with the external universe, but it is locally undetectable. A freely falling observer crossing the horizon experiences nothing special at that moment. Space-time is curved but smooth. Tidal forces exist, but for a 10 solar mass black hole, are not yet catastrophic. The probe's clocks continue to tick. Her instruments continue to function. She could, in principle, have crossed the horizon without even noticing, had she not been tracking her position carefully against the black hole's geometry. Early in the history of black hole physics, some researchers believed that the event horizon marked a region of violent phenomena, that an observer crossing it would be torn apart or incinerated or otherwise destroyed. This impression arose from artifacts of particular coordinate systems, mathematical descriptions that became singular at the horizon, not because physics became singular there, but because the coordinates themselves were poorly chosen. In other coordinates, Eddington-Finkelstein coordinates, Kruskal-Szekeres coordinates, Kerr coordinates, the horizon is revealed for what it truly is. A surface of no return, yes, but not a surface of immediate destruction. The probe has crossed into the interior of the black hole. She is now in the region between the outer and inner horizons, the region bounded below by the Cauchy horizon. Space-time here is bizarre by any ordinary standard. Radial directions have become time-like. The singularity lies in the probe's future rather than at a location she could avoid by steering, but the true strangeness still awaits. She continues to fall. The inner horizon approaches, the Cauchy horizon, and here, the mathematics begins to reveal something deeply troubling. The Cauchy horizon is not merely another event horizon. It is the boundary beyond which the deterministic evolution of spacetime ceases to hold. In the language of mathematical physics, it is the limit of Cauchy development, the farthest surface to which initial data can uniquely determine the future. Beyond the Cauchy horizon, the equations of general relativity become ambiguous. Multiple different futures are consistent with the same past. Predictability fails, but that is not the immediate danger. The immediate danger is light. Roger Penrose and W.A. Simpson argued in work dating back to the early investigations of black hole interiors that the Cauchy horizon of a black hole is a surface of infinite blue shift. Consider light entering the black hole from the external universe, light from distant stars, from the cosmic microwave background, from all the events that ever occur outside the horizon. As this light falls inward, it is blue shifted. Its frequency increases, its wavelength shortens, its energy grows. For an observer falling toward the inner horizon, this incoming radiation is compressed. The entire future history of the external universe, infinite as it may be, is blue shifted and concentrated. At the outer horizon, this effect is modest. An observer crossing the outer horizon sees the external universe somewhat blue shifted, but not catastrophically so. But as the observer approaches the inner horizon, the Cauchy horizon, the blue shift becomes extreme. The light from outside arrives with higher and higher energy. In the mathematical idealization of the Kerr metric, the blue shift becomes infinite at the Cauchy horizon itself. The energy of incoming radiation diverges. An observer attempting to cross the Cauchy horizon would be struck by an infinitely energetic flash of blue shifted radiation from the external universe. This is catastrophic. An infinite energy flux would destroy any physical object, and more than that, it would perturb the space-time geometry itself. General relativity is nonlinear. Energy creates gravity, and an infinite concentration of energy at the Cauchy horizon would create an infinite gravitational effect, warping the space-time, producing what some researchers have called a mass inflation singularity, a region where the Cauchy horizon itself becomes singular due to the accumulated energy of blue-shifted radiation. This was the Penrose-Simpson argument. The Cauchy horizon of any realistic black hole is unstable. It cannot survive the blue-shifted influx of radiation from the external universe. The smooth Cauchy horizon of the idealized Kerr metric, the one that appears on the Penrose diagrams with their infinite ladders of universes, is a mathematical fiction. The moment you include any perturbation, any infalling radiation, any matter crossing the horizon, any deviation from perfect axis symmetry, the Cauchy horizon develops a singularity, and if the Cauchy horizon is singular, then the interior structure of the Kerr solution beyond it, the ring singularity, the negative R region, the closed time-like curves, the passages to other asymptotically flat universes, becomes inaccessible, not merely hidden behind an information barrier, but walled off by a singularity that destroys any observer attempting to reach it. This is the Cauchy horizon problem, and it remains one of the deepest unresolved questions in black hole physics. But we are not yet ready to address it fully. That comes later. For now, we note only this. The probe, falling through a 10 solar mass Kerr black hole, faces her true danger not at the ring singularity, but at the inner horizon. The ring, if it exists, is avoidable. Geodesics can pass through the center of the ring without touching the singularity itself, as we discussed in an earlier section. But the Cauchy horizon cannot be avoided by any observer who passes through the outer horizon. It lies in the future of every interior trajectory. It is the gate through which all paths must pass to reach the deeper regions of the Kerr geometry. And according to the Penrose-Simpson argument, that gate may be impassable. The infinite blue shift transforms the Cauchy horizon from a mere boundary of predictability into a physical barrier, a wall of light, concentrated and compressed, arriving from the entire external universe with unlimited energy. The probe approaches the Cauchy horizon. If the idealized Kerr solution held perfectly, if the black hole were truly eternal, truly isolated, truly unperturbed by any external radiation, she might cross the inner horizon as smoothly as she crossed the outer. But no black hole in nature satisfies these conditions. Every black hole is bombarded by light from the cosmic microwave background. Every black hole forms through collapse, a dynamic process rather than an eternal static geometry. Every black hole is perturbed. What happens to the probe at the Cauchy horizon? Does the mass inflation singularity form? Is she destroyed by blue-shifted radiation before she can reach the ring? Or is there some mechanism, some physical process not captured in the classical analysis that permits passage? These questions remain open. The mathematics of the idealized Kerr solution says one thing, the physics of perturbations suggests another. We cannot observe the interior directly. We cannot send probes and receive their reports. We can only calculate, conjecture, and debate. But this much is certain. If the interior of a rotating black hole is anything like the Kerr metric describes, then the Cauchy horizon is the fulcrum. It is the surface where determinism fails, where blue-shifted light accumulates, where the structure of the extended solution, the ladder of universes, the closed time-like curves, the ring singularity itself, is either confirmed or denied. The probe's fate hinges on what happens there, and by extension, so does the fate of every question we have asked about the interior of rotating black holes. She falls onward, through the strange geometry between horizons, toward the inner horizon and whatever awaits beyond. The ring singularity beckons, or perhaps it does not exist at all, replaced by some other structure that nature builds in place of the mathematician's idealization. Either way, the journey continues. The mathematics permits it. The physics remains unresolved, and somewhere, at the heart of this rotating space-time, time itself may curve back upon itself. If the Cauchy horizon can be crossed, if the ring can be navigated, if the negative region opens as the equations predict. Somewhere in there, causality itself waits to be tested. The Cauchy horizon. This thin membrane of space-time, this boundary where prediction ends and uncertainty begins, had haunted physicists since the structure of the Kerr solution became clear. By the late 1960s, Roger Penrose had already established himself as one of the deepest thinkers in general relativity. His conformal diagrams had made the causal structure of black holes visually graspable. His singularity theorems had demonstrated that gravitational collapse must produce singularities under certain conditions. But Penrose was troubled by what his own mathematics revealed. In 1969, he formulated what would become known as the cosmic censorship hypotheses. There were two versions, a weak and a strong, and both addressed the same fundamental anxiety, that general relativity, left to its own devices, might produce pathological structures that undermine the theory's coherence. The weak version stated that no naked singularity should be visible from infinity. A singularity in this view must always hide behind an event horizon. Nature must clothe its most extreme geometries, preventing them from broadcasting their existence to distant observers. The strong version went further. It asserted that general relativity must be globally hyperbolic, that the universe must be deterministic, that no Cauchy horizon should persist in any physically realistic spacetime. The strong version demanded that surfaces like the inner horizon of a Kerr black hole must be unstable, that any perturbation must destroy them, converting them into singularities that block access to the acausal regions beyond. These were conjectures, not theorems. Penrose could not prove them. But he and others, Stephen Hawking, Robert Wald, Werner Israel, and many of the leading relativists of the era, believed that cosmic censorship represented the most important unresolved challenge within classical general relativity. If strong cosmic censorship failed, then general relativity would contain domains where determinism breaks down, where the future cannot be predicted from the past, where causality itself becomes ambiguous. For a theory that had been built on the premise of lawful, geometric necessity, such a failure would be profound. The physical argument seemed compelling. Consider what happens at the Cauchy horizon of a realistic Kerr black hole. Not the idealized, eternal vacuum solution that Kerr wrote down in 1963, but an actual black hole formed by gravitational collapse, embedded in a universe filled with light. As we discussed, radiation falling into the black hole is blue-shifted as it approaches the inner horizon. The mathematical analysis, developed by Penrose and Simpson, and refined by subsequent researchers, indicated that this blue shift grows without bound. Energy accumulates. The stress-energy tensor at the Cauchy horizon diverges, and when stress-energy diverges, general relativity responds with curvature. The geometry itself becomes singular. This is the mass inflation singularity. It forms not at the ring, but at the Cauchy horizon, and it forms for any black hole that receives even the faintest radiation from outside. The cosmic microwave background alone, the the remnant glow of the Big Bang pervading all of space at a temperature of 2.7 Kelvin would be sufficient. As long as any radiation crosses the outer horizon, the Cauchy horizon develops a singularity. For decades, this seemed to vindicate strong cosmic censorship. The beautiful interior structure of the Kerr solution, the ladder of universes, the ring singularity, the closed time-like curves, appeared to be mathematical artifacts, accessible only in an idealized solution that nature could never actually produce. Real black holes, perturbed black holes that actually exist, would have their Cauchy horizons converted to barriers. The deeper geometry would be walled off. But science does not settle its questions by consensus, however compelling the physical intuition might be. Mathematics has a way of surprising those who think they understand its implications. In 2017, Mihalis de Fermos and Jonathan Look published a result that challenged decades of thinking about the Cauchy horizon. Their analysis was rigorous, grounded in the formidable apparatus of mathematical relativity, and its conclusions were startling. Strong cosmic censorship, at least in the form Penrose and others had championed, might be violated. The technical details are intricate, but the essence can be stated simply. Dafamos and Luke constructed counterexamples to strong cosmic censorship, spacetimes in which the Cauchy horizon is singular but remains traversable. The singularity that forms is not like the singularity at the centre of a Schwarzschild black hole, where tidal forces diverge to infinity and any observer is crushed to a point. Instead, it is what mathematicians call a weak singularity, a boundary where certain curvature quantities diverge, but where geodesics can still be extended, where observers can still pass through. Imagine it this way. The Cauchy horizon becomes damaged by the infalling radiation, develops pathological features, but does not become an impenetrable wall. It scars rather than blocks. An observer crossing this weakly singular Cauchy horizon would experience unusual effects. Tidal forces might spike briefly, the geometry might become non-smooth, but the observer would not be destroyed. They could continue inward, toward the ring singularity and whatever lies beyond. This finding did not prove that the interior of real black holes is accessible. The analysis made specific assumptions about the form of the perturbations, and the question of whether these assumptions capture the full physics of realistic gravitational collapse remains contested. But it did demonstrate something profound. The question is genuinely open. Strong cosmic censorship, for all its intuitive appeal, for all the authority of the physicists who championed it, is not settled. The Penrose diagrams we drew in earlier sections show an infinite ladder of universes connected through the Kerr geometry. Each passage through the Cauchy horizon and the ring singularity leads to a new asymptotically flat region, a universe with different histories, different physics perhaps, reachable through the corridor inside the black hole. Strong cosmic censorship says this ladder is a mathematical fantasy, that nature builds a wall at the first rung. The Defamos-Look result says maybe not. And so the debate continues. Some physicists maintain that quantum effects not captured in classical general relativity will ultimately enforce cosmic censorship, that when we understand quantum gravity, the Cauchy horizon will prove rigorously impassable. Others point to the de Fermos-Look result as evidence that we should take the extended Kerr geometry seriously, that the ladder of universes might be more than a mathematical curiosity. The truth is that we do not know. The Cauchy horizon remains the hinge on which the entire interior structure turns, and after more than half a century of effort, we cannot say with certainty whether that hinge opens or remains forever locked. But the Cauchy horizon is not the only horizon in a rotating black hole story. There is another kind of horizon, not a geometric surface in space, but a temporal limit, a point in the black hole's future when it ceases to exist altogether. In 1974, Stephen Hawking made a discovery that transformed our understanding of black holes. Working at Cambridge, applying the principles of quantum field theory to curved space-time, Hawking demonstrated that black holes are not perfectly black. They radiate. The mechanism is subtle, and it occurs at the boundary between quantum mechanics and general relativity, a boundary where neither theory alone provides a complete description. Near the event horizon of a black hole, the intense gravitational field affects the quantum vacuum. In quantum field theory, empty space is not truly empty. It seethes with virtual particle pairs, flickering in and out of existence on timescales too short to observe directly. Near a black hole's horizon, Hawking showed, These virtual pairs can be torn apart. One particle falls through the horizon, carrying negative energy into the black hole. The other escapes to infinity, carrying positive energy away. From the perspective of a distant observer, the black hole emits radiation. Thermal radiation with a characteristic temperature inversely proportional to the black hole's mass. The larger the black hole, the colder it radiates. For stellar mass black holes, this temperature is unimaginably small, far colder than the cosmic microwave background, far too faint to detect with any conceivable instrument, but it is not zero. And because the escaping particles carry energy away, the black hole loses mass. This is Hawking radiation, and its implications are staggering. Black holes, which classical general relativity describes as eternal objects from which nothing can escape, are in fact slowly evaporating. They shed their mass, quantum by quantum, photon by photon, over timescales that dwarf the current age of the universe. A black hole with the mass of our Sun would take approximately 10 past 67 years to evaporate, a number so large that the universe would have grown cold and dark long before the process completed. But the principle stands: black holes are not forever. Given enough time, they will vanish. But Hawking's discovery was not entirely novel in its mechanism. 3 years earlier, in 1971, two Soviet physicists had already glimpsed part of the phenomenon. Yakov Zeldovich and Alexei Starobinsky, working in Moscow, proposed that rotating black holes ought to create and emit particles through a process they understood by analogy with classical physics. A spinning metal sphere, they reasoned, amplifies electromagnetic waves under certain conditions, a phenomenon called superradiance. Zeldovich and Starobinsky argued that a spinning black hole should do the same, extracting rotational energy from the ergosphere and emitting particles in the process. This insight connects to what happens to a Kerr black hole as it evaporates. Hawking radiation does not strip mass and angular momentum from a rotating black hole equally. The emission process operates asymmetrically, preferentially shedding angular momentum. As a Kerr black hole radiates, it spins down. Think of it as a kind of cosmic friction. The black hole's rotation creates an ergosphere, that region outside the outer horizon where spacetime itself is dragged into rotation. Within this ergosphere, superradiant processes operate, amplifying certain frequencies of radiation, extracting rotational energy and beaming it outward. The black hole loses not just mass but spin, and it loses spin faster than it loses mass. The consequence is that a Kerr black hole, over eons of evaporation, approaches the Schwarzschild limit. Its spin parameter decreases, the two horizons, inner and outer, move closer together, and the geometry shifts. The ring singularity, which exists only in rotating solutions, the closed time-like curves, the ladder of universes, all of these features are properties of the Kerr metric dependent on angular momentum. As the spin drains away, the black hole transforms, approaching the simpler, more austere geometry of a non-rotating hole. But this approach is asymptotic. A perfectly Schwarzschild black hole has zero angular momentum, and reaching exactly zero would require emitting the last quantum of spin. At that final moment, the black hole would still be evaporating, still radiating away its remaining mass. And here the deepest questions converge. What happens when a black hole evaporates completely? In classical general relativity, the answer seems clear. The black hole shrinks until its mass vanishes and the event horizon disappears. But inside that horizon, inside the collapsing geometry, there was a singularity. In a Schwarzschild hole, it is a point. In a Kerr hole, it is a ring. When the horizon evaporates away, what happens to that singularity? If the singularity persists after the horizon vanishes, it becomes naked, visible to distant observers, unshielded by any event horizon, violating cosmic censorship in its most dramatic form. The singularity would be exposed to the universe, a tear in the fabric of space-time that external observers could in principle study, approach, perhaps even interact with. This would be catastrophic for the coherence of general relativity. A naked singularity is a place where the equations break down, where curvature becomes infinite, where predictability fails. The entire framework of the theory depends on such breakdowns being hidden, censored, tucked safely behind event horizons, where their pathological properties cannot contaminate the external universe. So what happens? When the last quantum of Hawking radiation is emitted, when the horizon shrinks to nothing, when the black hole as a macroscopic object ceases to exist, does the singularity evaporate with it? Does it vanish in a final burst of radiation, the ring dissolving into energy that disperses into the surrounding space? Or does something remain, a remnant, a scar, a naked singularity exposed at last to an external universe that has waited since the black hole's formation to see what lay inside? We do not know. After 50 years of grappling with this question, after countless papers and conferences and debates, the final fate of a singularity during Hawking evaporation remains unresolved. The problem lies at the intersection of general relativity and quantum mechanics, a region where neither theory alone provides reliable guidance, where a complete theory of quantum gravity would be needed to give a definitive answer. We do not have such a theory. We have approximations, conjectures, plausible arguments, but no proof. Some theorists believe that quantum effects must enforce cosmic censorship, that some mechanism we do not yet understand prevents the singularity from ever becoming naked. Perhaps the singularity evaporates before the horizon does. Perhaps quantum gravity replaces the classical singularity with something else, a bounce, a transition to a new phase of spacetime, a structure without infinite curvature. Perhaps black holes do not evaporate completely, but leave behind remnants, stable objects with Planck-scale masses that contain whatever singular structures existed inside, safely wrapped in their own microscopic horizons. Others argue that cosmic censorship may simply fail, that naked singularities might form in nature, and that general relativity's inability to describe them is not a feature but a bug, a sign that the theory is incomplete. On this view, the naked singularity is not something nature must avoid, but something that points the way toward new physics, toward the theory that will eventually replace or complete general relativity. The ring singularity inside a Kerr black hole makes this question particularly acute. A point singularity, as in the Schwarzschild solution, has zero size. There is nowhere for it to go, nothing for it to become except energy dispersed into radiation. But a ring singularity has structure. It has a circumference, defined by the black hole's original angular momentum. It encloses a region, the negative R domain, where closed time-like curves exist. When such a structure evaporates, when the spin that defines it drains away, what remains? Perhaps nothing. Perhaps the ring, like the rotation that sustained it, is merely a transient feature, dissolving as the black hole spins down. Perhaps by the time the black hole approaches the Schwarzschild limit, the ring has already transformed into something else, a point, a quantum fuzz, a feature too small to retain its ring-like character. Or perhaps the ring persists, shrinking as the black hole evaporates, maintaining its topology even as its size diminishes. In that case, the final moments of evaporation would confront us with a ring singularity of microscopic scale, carrying all the exotic geometry of the Kerr solution, the closed time-like curves, the passages to other regions, in a package small enough to exist without a macroscopic horizon. A naked ring singularity exposed to the universe, encoding causality violations in a structure visible to external observers. The honest answer is that we do not know which scenario is correct. The mathematics of Hawking evaporation, rigorous as far as it goes, does not extend reliably to the final moments when quantum gravitational effects dominate. We can calculate the early stages of evaporation with confidence, but the endgame remains obscure. And so the question that has haunted quantum gravity since 1974 remains unanswered. When the last quantum of radiation is emitted, what happens to the ring singularity inside? Does it evaporate with the whole, or is it exposed, a naked singularity, violating cosmic censorship, revealing the interior structure that a horizon once hid? This question might have remained purely academic, a puzzle for theorists to argue over without resolution, indefinitely suspended between competing intuitions. But in December 2023, an unexpected voice entered the debate, Roy Kerr. 60 years after he first wrote down the metric that bears his name. 60 years after that afternoon in Dallas when Achilles Papapetrou interrupted the session to declare the importance of what a young New Zealand mathematician had found, Roy Kerr submitted a paper with a provocative title, Do Black Holes Have Singularities? The title itself was a challenge. The entire edifice of black hole physics, the singularity theorems, the cosmic censorship conjectures, the decades of debate about the Cauchy horizon and the interior structure, had been built on the assumption that black holes do contain singularities. Penrose had proven that singularities must form under certain conditions. Hawking and Penrose together had generalized these theorems. The singularity was supposed to be an unavoidable consequence of gravitational collapse, a feature that general relativity predicted with mathematical certainty. And now Kerr, whose metric had revealed the ring singularity in the first place, was questioning its existence. The paper's abstract stated it plainly. There is no proof that black holes contain singularities when they are generated by real physical bodies. This was not a minor technical quibble. This was an assault on foundational assumptions. Kerr was arguing that the singularity theorems, the crown jewels of classical general relativity, the results that had helped earn Penrose his Nobel Prize, did not actually prove what everyone assumed they proved. The argument turned on a subtle but crucial distinction. The singularity theorems prove that gravitational collapse produces geodesic incompleteness. This means that certain paths through spacetime, the trajectories of freely falling observers, the paths of light rays, cannot be extended indefinitely. They terminate. They reach a boundary beyond which the mathematics cannot continue. For 60 years, geodesic incompleteness had been taken as synonymous with singularity. If paths cannot be extended, the reasoning went, it must be because they encounter something pathological, infinite curvature, infinite density, a singularity. The incompleteness is the symptom. The singularity is the disease. Kerr challenged this identification. Geodesic incompleteness, he argued, does not necessarily imply infinite curvature. It indicates a boundary. Yes, but that boundary need not be a physical singularity. The paths terminate, but they might terminate at a surface rather than a point of infinite density, at a structure that is unusual but not infinitely pathological. To make his case, Kerr pointed to counterexamples within his own metric. There are geodesics in the Kerr solution that are asymptotic to the event horizon, curves that approach the horizon without ever crossing it, taking infinite proper time to reach it. These geodesics are incomplete in the formal sense. They cannot be extended beyond the horizon within a finite parameter range, but they do not encounter any singularity. They simply approach a surface and never quite reach it. If incompleteness can occur without singularity in these cases, Kerr argued, why should we assume that the incompleteness at R0 necessarily indicates a singularity? Perhaps the ring singularity of his idealized, eternal vacuum solution is itself an artifact, a feature of the mathematical idealization that does not persist in physically realistic collapse. This is a subtle point, and it requires careful attention. The Kerr metric describes an eternal, rotating, vacuum black hole. It does not describe the process by which such a black hole forms. When a real star collapses, the spacetime is not the Kerr metric throughout. There is matter, there is dynamics, there is a transition from a pre-collapse star to a post-collapse black hole. The question Kerr raises is whether this dynamical process produces the same interior structure that the idealized eternal metric exhibits. The no-hair theorem states that all stationary black holes settle down to the Kerr geometry. After the collapse is complete, after gravitational waves have carried away asymmetries, the external geometry of any rotating black hole approaches the Kerr metric with arbitrary precision. But this theorem applies to the exterior, the region outside the event horizon, the part accessible to distant observers. What happens inside during and after collapse is not constrained by no-hair. Kerr's argument, in essence, is that the perfect symmetry of his vacuum solution, the precise, eternal, idealized rotating spacetime, does not occur in physical reality. Real collapse is messy. Real matter has pressure, viscosity, electromagnetic fields. Real collapse does not produce the infinitely thin, perfectly circular ring singularity that the mathematics of the Kerr metric describes. Something else forms instead, a structure that is perhaps singular in some weak sense, perhaps merely extreme, but not the naked pathology that the idealized solution implies. Roger Penrose claimed 60 years ago that trapped surfaces inevitably lead to geodesics of finite affine length, paths that cannot be extended indefinitely. Penrose and Hawking then asserted that these incomplete geodesics must end in singularities. Kerr is now saying, not necessarily. The assertion that geodesic incompleteness requires a singularity is not a theorem. It is a conjecture, a physical interpretation, an assumption that has hardened into orthodoxy without ever being rigorously established. The implications, if Kerr is right, ripple through everything we have discussed. The ring singularity may not exist. The closed time-like curves in the negative R region may not be physically realizable. The ladder of universes shown in the Penrose diagram may be a mathematical fantasy, not because the Cauchy horizon blocks access, but because the interior structure the ladder connects to was never there in the first place. This does not resolve the Cauchy horizon problem. If anything, it deepens it. If the ring singularity does not form, what does form? What replaces it? Kerr does not claim to know. He claims only that the standard picture, the picture built from his own 60-year-old solution, may be wrong. The paper is a challenge to the field, not a resolution. It reopens questions that many had considered closed, or at least narrowed to technical disputes about the Cauchy horizon's stability. Kerr is saying something more radical. Maybe we have been asking the wrong questions. Maybe the interior of a rotating black hole is nothing like the Kerr metric describes. Maybe singularities, in the sense that physicists have meant the term for 60 years, do not form at all. At 90 years old, the man who gave us the ring singularity is telling us we should not believe in it. This is not the end of the story. It is, in a sense, only the beginning of a new chapter, a chapter in which the foundational assumptions of black hole physics are being re-examined, in which the certainties of the 20th century are giving way to the uncertainties of the 21st. The Kerr metric remains the best mathematical description of rotating black holes. Every observed black hole from Cygnus X1 to M87 is described by this solution. The ring singularity, the Cauchy horizon, the ladder of universes, these are all mathematical features of the metric that Kerr wrote down in 1963. But whether these mathematical features correspond to physical reality is a question that Kerr himself, 60 years later, has declared open. The mathematics permits many things. The physics may permit fewer, and until we have a complete theory of quantum gravity, until we can probe the interiors of black holes with something more than thought experiments and equations, we will not know which mathematical features are physical truths and which are artifacts of idealization. The ring singularity beckons, as it has beckoned since 1963. It promises passage to other universes, closed time-like curves, violations of causality itself. But the man who discovered it now doubts that it exists at all. And in that doubt lies the honest state of our knowledge, profound, hard-won, and radically incomplete. The doubt does not sit quietly in the literature. It lands in a field already riven by fractures, a discipline that has spent the last half-century wrestling with paradoxes that seem to multiply faster than they can be resolved. Kerr's challenge arrives not in isolation, but in a landscape shaped by decades of crisis, of arguments that have forced physicists to question whether the elegant equations of general relativity can be trusted all the way down to their smallest predictions. Consider the black hole information paradox, which has haunted theoretical physics since Stephen Hawking first described the thermal radiation that bears his name. If a black hole evaporates completely, as Hawking's calculations suggest it must, what happens to the information encoded in everything that fell in? Quantum mechanics demands that information be conserved. The universe, at its most fundamental level, is supposed to be a closed book in which nothing is truly lost. But Hawking's original analysis implied that the radiation escaping a black hole is perfectly thermal, carrying no information about what formed the hole in the first place. The star that collapsed, the planets it may have consumed, the astronauts who fell past the horizon, all of it reduced to featureless heat, as if the universe had developed a case of selective amnesia. For decades, physicists argued about whether this paradox was real or apparent, whether some subtle mechanism might smuggle information out of the black hole in ways Hawking had not anticipated. The debate seemed almost theological at times, a dispute about bookkeeping in a realm no experiment could probe. But in 2012, the argument took a sharp and disturbing turn. Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully, a collaboration that came to be known by their initials AMPS, published a paper that sharpened the paradox into something that looked almost like a contradiction. They argued that if information is preserved, if the radiation escaping a black hole is subtly entangled with the interior in a way that allows information to escape, then the smooth, uneventful horizon predicted by general relativity cannot exist. Instead, an infalling observer would encounter a firewall, a curtain of high-energy radiation at the event horizon that would incinerate anything attempting to cross. The firewall argument was not a claim about what definitely happens at a black hole horizon. It was a demonstration that three things physicists had assumed to be simultaneously true could not all be true together. You could have a smooth horizon, or you could have information preservation, or you could have the standard rules of quantum field theory and curved spacetime, but not all three. Something had to give, and no one could agree on what. The firewall debate raged through the theoretical physics community, spawning hundreds of papers, careers worth of argument, and no consensus. Some physicists argued that the horizon must be smooth and that the paradox revealed a flaw in our understanding of quantum entanglement at cosmological scales. Others accepted the firewall as real, a barrier of flame guarding the entrance to the black hole's interior. Still others proposed that the entire framework needed to be replaced, that black holes were not the object's general relativity described at all. This was the context into which Kerr's 2023 paper arrived. A field that had already learned to distrust its most fundamental predictions, that had spent a decade arguing about whether the event horizon itself was a barrier of fire or a passageway to regions unknown. The ring singularity, the Cauchy horizon, the ladder of universes, these were structures that lay beyond the event horizon, in a region that the firewall argument suggested might not even be accessible. If the horizon itself was in question, how much more uncertain was everything that lay beyond it? And the ring singularity is not the only feature of black hole interiors that physicists have learned to doubt. In the years since Kerr's solution first revealed the geometry of rotating spacetime, alternative models have emerged, models that attempt to describe what might actually occupy the region where the singularity is supposed to sit. Loop quantum gravity, one of the leading approaches to quantizing spacetime itself, suggests that the singularity might be replaced by a quantum bounce, a region of extreme but finite curvature where the collapsing matter rebounds rather than crushing down to infinite density. In this picture, the singularity is an artifact of classical physics, a prediction that breaks down when quantum effects become significant. The ring might be smeared out, softened, replaced by a structure that is strange but not pathological. String theory offers its own alternative, the fuzzball model, in which the entire interior of a black hole is replaced by a tangled web of quantum strings and brains, extending all the way to the horizon. In this picture, there is no empty interior, no singularity at the centre, no ring through which an astronaut might pass. The black hole is a solid object, or rather an object made of quantum fuzz with no void at its heart. The Penrose diagram of the Kerr metric with its ladder of universes and its time-like ring would be not just physically unrealizable but categorically wrong, a description of a geometry that nature never permits. These competing approaches do not agree with each other. Loop quantum gravity and string theory are rival programs built on different mathematical foundations, making different assumptions about the nature of space-time at the smallest scales. What they share is a conviction that the singularity predicted by classical general relativity cannot be the final answer, that something must intervene before matter crushes down to infinite density. The ring singularity of the Kerr metric on these views is a placeholder, a sign pointing to physics we do not yet understand, not a literal description of what sits at the heart of every rotating black hole. And then there is Kerr's own position, which stands apart from both the classical orthodoxy and the quantum alternatives. Kerr is not claiming that quantum gravity dissolves the singularity. He's claiming something more unexpected, that classical general relativity, properly interpreted, never predicted a singularity in the first place. The Penrose-Hawking theorems, the foundational results that most physicists cite as proof that singularities are inevitable, prove only that geodesics cannot be extended indefinitely. They prove that something goes wrong, that the smooth fabric of space-time cannot continue forever into the interior of a collapsing star. But they do not prove that the something that goes wrong is a singularity in the traditional sense, a point or ring of infinite curvature where the equations break down entirely. Kerr's counterexamples, the geodesics he exhibits in his 2023 paper, do not end in singularities. They approach the event horizon asymptotically, spiralling inward forever without ever reaching a pathological terminus. If such geodesics exist in the Kerr metric, and Kerr demonstrates mathematically that they do, then the claim that all geodesics must end in singularities is false. The theorems are not wrong, their interpretation is. Geodesic incompleteness is not the same thing as singularity. This is a subtle point, and it has not been universally accepted. Many relativists remain committed to the classical picture, arguing that Kerr's counterexamples are special cases, that generic geodesics in a collapsing spacetime do terminate in singularities, that the physical process of stellar collapse inevitably produces the pathologies that the idealized Kerr metric describes. The debate is technical, hinging on questions about the measure of geodesics, the stability of various features under perturbation, the precise definition of what it means for a spacetime to be singular. But the existence of the debate itself is significant. For 60 years, the ring singularity was treated as an established feature of black hole physics, a consequence of Kerr's solution that, however strange, was mathematically secure. Now the man who discovered it is questioning whether it was ever really there. The field cannot agree on whether the singularity is dissolved by quantum effects, blocked by a firewall, replaced by a fuzzball, or simply absent from the classical theory in the first place. The fracture lines run deep, and they are not merely academic. They concern the most fundamental question one can ask about the objects that anchor galaxies and warp space-time itself. What is inside a black hole? The honest answer, the answer that emerges from decades of argument and counter-argument, is that no one knows. The ring singularity of the Kerr metric is a mathematical feature of an exact solution. Whether it corresponds to anything physical depends on questions that neither observation nor theory has yet resolved. The Event Horizon Telescope can image the shadow of M-7's Kern, the silhouette of the photon sphere against the glow of accreting matter, but it cannot see past the horizon. Gravitational wave detectors can hear the chirp of merging black holes, the ringing of space-time as two horizons become one, but they cannot probe the interior. Everything beyond the event horizon remains inference, extrapolation, educated speculation grounded in mathematics that may or may not describe reality. This is not a failure of science. It is the honest condition of a discipline confronting phenomena at the edge of its reach. The Kerr metric is one of the most exact solutions in the history of physics, a closed-form answer to the notoriously difficult Einstein field equations. For nearly half a century, from 1916 to 1963, physicists could solve those equations only for the simplest case, a static, non-rotating, spherically symmetric mass. Schwarzschild's solution, elegant as it was, described an object that does not exist in nature. Every star rotates, every collapsing core carries angular momentum into its final state. The Schwarzschild black hole, with its point singularity and its single horizon, was an idealization waiting to be superseded. Kerr's achievement was to find the solution that superseded it. Working with a rotating ansatz, exploiting symmetries that had eluded others, he derived the metric that describes every astrophysical black hole we have ever observed. The mathematics is not approximate. It is not a perturbation series, not a numerical solution, not a linearization valid only in some limit. It is exact, and its exactness is both its power and its peril. An exact solution carries all its features with equal mathematical weight. The ring singularity, the Cauchy horizon, the closed time-like curves, the ladder of universes, all of these are consequences of the same equation, derived with the same rigor. If the metric is physically accurate, all of these features must be physically real. If any of them fails to correspond to nature, the metric's authority is compromised. Subrahmanyan Chandrasekhar, the Nobel laureate who devoted his later career to the mathematical theory of black holes, wrote of the Kerr solution with something approaching awe. The most shattering experience, he said, has been the realization that an exact solution of Einstein's equations of general relativity, discovered by the New Zealand mathematician Roy Kerr, provides the absolutely exact representation of untold numbers of massive black holes that populate the universe. Chandrasekhar understood the strangeness of this situation, that a single formula, written down by a 29-year-old mathematician in the back rooms of a Texas symposium, could describe objects scattered across billions of light years, anchoring galaxies and consuming stars with a geometry specified to infinite precision. But exactness in mathematics is not the same as truth in physics. The Kerr metric is a vacuum solution. It describes space-time around a rotating mass, but it assumes that mass has already collapsed, that the singularity, if singularity there is, already exists. that the geometry has settled into its final stationary form. It says nothing about the process of collapse, the turbulent dynamics of a star crushing itself into oblivion. It assumes perfect axial symmetry, a rotating object with no lumps, no perturbations, no deviation from idealized form. Real black holes form from real stars, which are messy, asymmetric, threaded with magnetic fields and racked by convection. The Kerr metric is the end state, the idealized attractor that all these messy processes are supposed to approach. Whether they approach it closely enough for the interior structure to match the mathematical prediction is a question that the metric itself cannot answer. And so we return, as we must, to the ring itself. A one-dimensional curve in the equatorial plane of a rotating black hole, infinitely thin, of finite circumference, where the equations of general relativity predict infinite curvature. Unlike the point singularity of a Schwarzschild black hole, which is a moment in time, a future that all infalling matter must meet, the ring is a place in space, a structure that can in principle be avoided, a portal whose centre is a doorway to regions of negative radial coordinate, to spaces that their mathematics says are asymptotically flat to other universes stacked in an infinite ladder, extending through the conformal diagram. This is the image that has captivated physicists and science fiction writers alike. The ring as gateway, the black hole as bridge between worlds. It is an image grounded in rigorous mathematics, derived from Einstein's field equations with no approximations or hand-waving, and it may be entirely fictional. Not fictional in the sense of being poorly motivated or mathematically inconsistent, fictional in the sense that the physical universe may not instantiate the structure that the mathematics describes. The ring singularity is a solution feature, not an observational datum. No one has ever detected a ring singularity. No one knows how one could. Every black hole observation we have made is consistent with the Kerr metric's external predictions. The shape of the shadow, the frequency of the gravitational waves, the behavior of orbiting matter. But the external predictions do not depend on the interior structure. A black hole whose interior was a fuzzball, or a quantum bounce, or some structure yet unimagined, would look the same from outside as long as it possessed the same mass and spin. The event horizon hides the interior perfectly. Whatever lies within is sealed away from observation by the very geometry that defines the horizon's existence. This is the epistemological situation we confront, a mathematical solution of perfect exactness, describing objects of unambiguous reality, whose interior predictions cannot be tested by any observation we know how to make. The ring singularity is there in the equations. Whether it is there in the universe is a different question, and it may remain unanswered for a very long time. Kerr's 2023 paper does not resolve this question, it sharpens it. By challenging the interpretation of the Penrose-Hawking theorems, by exhibiting geodesics that do not terminate in singularities, Kerr has reopened a debate that many considered settled. The singularity theorems were supposed to be the definitive statement, the proof that general relativity predicts its own breakdown, that somewhere inside every black hole the equations must fail. Kerr is saying, look again. The theorems prove less than we thought. The singularity was always an assumption dressed as a conclusion. If he is right, the implications are profound. The closed time-like curves that thread through the negative R region of the extended Kerr spacetime, the paths that loop back on themselves permitting travellers to meet their own past, may be artifacts of an idealization that nature never instantiates. The ladder of universes, the infinite chain of asymptotically flat regions connected through the ring, may be a mathematical structure with no physical counterpart. The most disturbing features of the Kerr metric, the features that have kept physicists awake at night for 60 years, may be no more real than the frictionless planes of introductory physics, useful for calculation, misleading as descriptions of reality. But we do not know. That is the point, and it must be stated plainly. We do not know whether the ring singularity is physical or mathematical, whether the interior of a rotating black hole is anything like the Kerr metric describes, whether the passages to other universes are real or illusory, whether causality is violated in the depths of cosmic gravitational engines or preserved by mechanisms we have not yet identified. 60 years after Kerr's discovery, the interior of a rotating black hole remains one of the deepest mysteries in physics. The equations sit on the page, elegant and exact. The ring traces its infinitely thin curve in the equatorial plane, a boundary where curvature becomes infinite and the theory perhaps breaks down. or perhaps it does not. Perhaps the ring is a sign pointing to new physics, quantum gravity effects that smooth the singularity into something tamer. Perhaps it is an artifact of idealization, a feature of the eternal vacuum solution that collapse from realistic matter does not produce. Perhaps Kerr himself is right, and the singularity was never required by the theory in the first place. We are left with the mathematics, which does not lie, but also does not interpret itself. We are left with observations of black hole exteriors, shadows and waves and jets of accreting matter that tell us nothing about what lies within. We are left with thought experiments and theoretical arguments, Penrose diagrams that map infinities onto finite pages, Hawking radiation that may or may not preserve information, firewalls that may or may not exist, and we are left with the ring, beckoning at the centre of every rotating black hole in the universe, a structure so simple it can be written in a single equation, and so strange that 60 years of contemplation have not exhausted its mysteries. It promises passage to other worlds, it permits violations of causality, it may not exist at all. This is not resolution. This is the actual state of human knowledge, the frontier where understanding meets the unknown. The Kerr metric is a triumph of mathematical physics, an exact solution that describes objects observed across the cosmos. Its interior features, the ring, the horizons, the closed curves, the ladder of universes, are logical consequences of the same equations. Whether nature permits what the mathematics describes is a question that remains open, genuinely open, contested by the very person who discovered the solution 60 years ago. The black holes are real. They anchor the galaxies, they consume stars, they merge in collisions that ring spacetime like a bell. They rotate, every one of them, carrying angular momentum that persists from the stars that formed them. They are described by Kerr's metric, his formula of 1963, his gift to a physics that did not immediately recognize its value. But the ring at their hearts remains an image held in mathematics, not observation. We cannot see it, we cannot probe it, we can only calculate what it would mean if it were real, and argue about whether the calculation corresponds to nature. The argument continues, sharpened by Kerr's own late intervention, unsettled by paradoxes that multiply faster than they resolve. This is where we leave the story, not with an answer, but with the question in its sharpest form. A ring of infinite curvature sits at the centre of the equations that describe every black hole ever observed. It may be the doorway to infinite universes, it may be a mathematical phantom. It is certainly the strangest feature of one of the most exact solutions in the history of physics, and its reality or unreality remains, in the honest assessment of the field, unknown. The ring waits, as it has waited since Roy Kerr first wrote down its equation in the winter of 1963. It waits for the theory that will finally say whether it exists, for the observation that cannot yet be made, for the resolution that this generation of physicists may not live to see. It is a question mark drawn in the fabric of space-time itself, and it will not stop asking until we find a way to answer. And perhaps that is enough. Perhaps it is appropriate that a solution this exact describing objects this strange should leave us not with certainty but with vertigo, the precise, earned discomfort of standing at the edge of what is known and staring into the void that the equations have mapped but cannot explain. The ring's singularity may be the most important non-answer in physics, a feature so extreme that its reality or unreality tests the foundations of the theory that predicts it. Whether it is there or not, we have learned something profound from its presence in the mathematics, something about the limits of general relativity, the necessity of quantum gravity, the strange terrain where our best theories break down or transcend themselves. Roy Kerr is 90 years old. He has lived to see his solution confirmed by observation, honoured by the detection of gravitational waves and the imaging of black hole shadows. He has also lived to challenge its most famous feature, to argue that the singularity he seemed to discover may never have been required. This is not a contradiction. It is the posture of a scientist who knows that equations are tools, not oracles, that the mathematics serves understanding, and understanding must ultimately be tested against reality. The ring endures in every textbook, in every Penrose diagram, at the centre of every calculation about rotating black holes. It endures because the equations demand it, and the equations are exact. Whether nature obeys those equations all the way down into the deepest core of spacetime's most extreme objects is a question the ring itself cannot answer. It waits. It has always been waiting. And we, who have followed its geometry from a Dallas symposium to the shadow of M87, from the theorems of Penrose to the doubts of Kerr himself, are left to wait alongside it, knowing what the mathematics says, uncertain what the universe means, standing at the threshold of a doorway that may lead to infinite worlds or may lead nowhere at all. The ring singularity turns in the dark, at the heart of every spinning black hole, silent and exact and profoundly, irreducibly unknown.